Yep, that's cool. And I'm starting the stream now, so you'll just see a black stream. I need to also put something. It says starting. I need to put like a text thing up to say we'll be live in a minute or something like that. Live in a couple minutes. So, how do I do that? Well, I don't know, but well, I have to see what's going on here. So it's starting. I see it starting, and
I see Bill's.
Yeah. Okay. Here goes mine. And
there we go.
And now I just have to get my chat and make it pop out.
Ladies and gentlemen, welcome to the SkyTour LiveStream with Mark D'Antonio.
Wow, you sound so cool.
I am professional tonight. I am a radio disc jockey from St. Louis, Missouri.
By the name of Fred Self.
I am Brad Pitt's brother, Stu.
Hey, that was good. Very funny. Very, very funny.
Stu Pitt, nice to meet you.
Yeah, that's it, right? All right, so.
Everybody's probably over there watching Bill. He's having fun. My man is having fun.
Oh, he's having a ball with his little, all the new facts that he's learned about that camera. He's like, oh, I can't believe it does that. I can't believe it can do that.
I have you on one feed and I have him on the other one.
Do you?
Yeah. It literally looks like he's standing outside and it's like noon. The way he has his camera settings on.
Yeah. Yeah. Well, that's I actually did teach him a few things. Hey Amanda, I see Amanda's in the room now.
Yeah, by the way, people in the chat see Keith is echoing, so it is something on your end.
It is. My end?
Yeah, because she says now I'm echoing, and I don't have any sound on whatsoever.
Interesting. So that means time to figure this out. How about that? Oops. That didn't work. Are you there?
And I can't hear it on my end.
I can't hear it either.
So
Keith is still echoing, huh?
Echo.
Uh-oh.
There's only one way to tell for sure.
Yeah, and if you hear two of those, or you hear them in sequence with each other.
Trying to figure out what it might be.
Yeah, me too. I can't tell right now. Well, we're gonna try and figure that out because that's unacceptable. And the other SkyTour LiveStream may actually figure out that problem.
I think he did back in 2007 already.
Oh, you think so?
Yeah, we're way behind.
Yeah. So did anybody mention anything to you about cyberbullying today?
Cyberbullying?
Yeah, did you hear from our friend and he did talk to you about cyberbullying?
No, but I'm telling you what, I will be watching the thumbs down because I have software now that I can see who's thumbing down.
Oh, really? That's a good thing. That's a funky thing.
Hold on, I'm gonna listen to the feed real quick and just see what I can tell from that to see if I might be able to tell where the echo is coming from.
All right.
So I'm gonna mute out for a minute just on the microphone.
No problem.
Yeah, it's all you.
Hey,
just do it.
Me. It's not my stream. Oh wait, yes it is.
It'll only be for like 5 seconds.
Okay, no problem. I'm still setting up the telescope to make sure that I get the alignment correct. But it's not quite dark enough yet for me to use my alignment stars.
Well, that's the thing. I'm not hearing an echo at all.
You're not? Not in the live stream?
No, I just clicked on the YouTube video and I heard our conversation, and I'm not hearing any echo at all.
Well, you might want to check with the people in the stream that you're saying that you are echoing, and have them turn off their freaking computer sound, or if they're listening with headphones. I don't know what's going on. Okay, select the start debate. Yes, that's what I'll do. Interesting. Well, if you're not echoing, who is? I don't get that. I do not get that. Huh.
Yeah, I don't hear it.
Well,
They say they just hear a little bit of reverb. So it's not as bad as what it was with Bill last night. Like, it's not a massive.
I suspect that's got to be something Bill's doing.
Well, what are you listening to me on?
Headphones. I have you on my headphones. For
Okay,
obvious
so that
reasons,
would
because that's the right thing to use. I can't be listening to you on a speaker. That wouldn't work.
Yeah, Amanda. As I said, I just listened to the stream, and my vocals sound fine. Mark sounds like a little open area just because he's in the dome in there. There's a lot of noise in the background, but I didn't hear any echo at all.
So I actually have the chat in a pop-out window, so I can maybe see it when I get down near it. But right now I can't. I'm just trying to figure out where the star is I'm trying to align on. Oh, that's darn close.
I should ask if it's buffering for anybody, because it's buffering for me on my end.
How is it buffering?
That's just a normal YouTube buffering.
Oh, it says it's just like doing the circle thing?
Yep.
I get that with your stream all the time. So I wonder if it's my internet.
It's possible. Is it buffering for anybody else?
Maybe they shall tell you. Alright, so we're gonna center this guy. I'm just doing an alignment to get this all straightened out, and then once we align, off we go into the wild blue yonder.
Yeah, we do have some people it's buffering for too.
I wonder why.
Yeah, I mean, you're just putting audio across. It's not like you even have a load on it or anything.
Yeah, I don't even have the stream going yet. So I don't know why that would be buffering unless that's the whole thing.
It's gotta be the output settings on there.
You think so?
Yeah.
Okay.
Let me see. You actually might have to take it down some depending on what you said. Your internet speed is
It's like 25.
is 25 down and how many up?
I don't remember. Crap. I don't remember. That's me not remembering.
Well, if you go into OBS settings,
Yeah.
you should see video bitrate somewhere there,
Okay.
and let me know what it says.
All right. Why don't I do that now while the telescope is hunting for the star and the Big Dipper that I need. Okay. Okay. Into the OBS settings.
Yep. Just click settings, and then it should say video bitrate when it is on the output.
Well, actually, I'm also having an FPS of 60 frames per second.
Drop it to 30. You don't need 60.
Okay.
That's probably your main trouble.
Well, let's try that because and I can do that kind of on the fly here, though. So if I go to video, SPF. I got SPF 90, but I'm going to drop it to 30, and then see what happens. Okay, it's now 30. I shall apply it.
Yep.
And hit OK, and see.
And then there should be, as I said, when you click settings, there should be a thing called output, and then you should see video bitrate somewhere.
All right, we're gonna do that next. Let's go to settings and go to outputting, broadcast settings, encoding, video. I don't have. Where would that be under?
It would be under output.
Okay, there's no output per se.
Okay. Well, just click on each one of them and see if you can find something that says video bit rate.
All right. Replay buffer length. No, that's not it. No.
Replay buffer length.
Yeah.
No, that's for recording probably.
Yeah. Okay. Browser. That won't be browser. Quick sync encoder. No.
What was that?
Quick sync encoder.
What's it say? What's it say the setting is for that?
Well, it's using whatever's defaulted. It says CBR, which is grayed out and is defaulted. And I can select use custom parameters. No, I can't select that. It won't let me.
Nah.
So I can't do anything there. So what's under advanced? Yeah, multi-threaded optimizations, process priority class normal.
Yeah, because there's a well, in OBS Studio there's a thing that says streaming, and then you have your video bitrate encoder settings, and then your audio bitrate you can adjust as well.
Yeah. It says for the network, bind to interface, latency tuning factor is 20.
Chat, let us know if it stopped buffering since we put it down to 30 frames per second. Just let us know if it's been buffering for you. If it hasn't, that probably fixed it.
Custom X264.
Yes, it should be. Well, on mine, it's right above that, but yours is going to be different.
What's that?
Like that software X264 is right below the video bitrate option on mine.
Okay. I have keyframe interval, but that was okay. Encoding profile is high, and CPU preset's very fast.
You said encoder what?
Encoding profile is on high, and it could be on main or high, and then
you should be able to click that, and you should have a lot of options there.
Not
right?
under encoding profile. I have main or I have high.
Okay.
And to X264 CPU preset is on very fast.
I have mine on ultra fast.
All right, I can try that.
That uses less CPU.
All right, warning: severe negative effects on stream quality and CPU usage. Don't do this unless you really want to do this. Are you sure you really want to do this? You are a jerk if you try this now. Wait, what?
You can always set it back if anything.
I guess I can. So I did it.
Well, people in the chat are saying that it hasn't buffered since you switched it to 30 frames.
Oh, so maybe I should have just left everything alone.
Yeah, I mean, you actually could have. I mean, if it starts doing it again, then we'll start looking at doing the encoder stuff. But,
well, I already changed it to ultra fast. Should I change it back?
No, I mean, that's fine. It's just going to use less CPU power, that's all.
Okay. And the buffer, the thing might be a little weak. Okay. So that gave me time to see LK. Oh, come on. What's that cloud doing there? You're not going to believe this. I actually got a patch of clouds moving through, but only clouds. So let's hope that...
You had to say something, didn't you?
You know, it happens every time.
Yep.
All right, well, let me just go...
Aren't we just talking about that before we came on air? We're like, yeah, we're going to get some of that daytime heating of clouds just going to appear out of nowhere.
And they do. All right, so let me just get this last bit here. We get LK'd in.
Okay, ladies and gentlemen, I believe we have fixed it. We dropped him to 30 frames per second because he really has no need for 60 frames a second. So 30 frames seems to be working. Everybody seems to be good. We're not buffering at all. Thank you to whoever invented 30 frames per second. I think it was done back in 2007.
Yeah, how about that?
Somebody invented it, and it sure as hell wasn't us, Mark.
No, because we tend to mess things up when we do this.
Yeah, and we all know that Paul's better at this than you are. I just want to let you know that right now.
Hey, you know what? I might be an astronomer, but I'm not a broadcaster.
You are not a well, you're gonna be by the time I'm done with
We're
you.
gonna get this done. If you could just see the strange gyrations that I'm going through right now.
I don't want to hear anything about you and any kind of gyration.
You know what? That's probably wise. I'm trying to just get this last star alignment done. There we go. I got you. All right.
All these people in the chat are like, all right, where's the screen at?
I know.
Holy crap! I didn't need that eardrum. Screw it.
Okay. Well, it's no problem. The line was successful, and I'm now going to start the camera feed.
Ladies and gentlemen, we're going to tour the cosmos with Mark D'Antonio here on the SkyTour LiveStream 2017.
At the EIB network.
On the EIB network.
That's exactly how it goes, ladies and gentlemen. All right, step one. We take out the gigantic...
we just started buffering again. What the...
That's open fast, too. Well, let me see what I can do here. Now, once I get the camera in place, we'll see what happens. It might not... It might be free of that.
The buffering is actually a lot slower than it was before. Like it's coming, like it's off and on real quick. You might even be able to drop it down to a slower frame rate yet.
All right. Well, the other problem is that I'm not doing any actual frame rate at the moment. Remember, I'm not showing any. I'm not doing anything yet. That is to say, I'm not actually streaming anything yet.
So it is probably the encoder settings.
Yeah, there's nothing coming out of the camera, nothing going through HDMI yet. And now that's changing. So I'm adding now something, and I'm going to see what we have for focus. Oh, look at that. That's not a mouse, is it? That's actually the, oh cool, I got a star, yay! Nice. All right, so what's funny is it actually showed up in focus already because I set the focus ahead of time, so I want to see how close I was. Did I just hear you go?
And we have a little star dead center.
Yeah.
And what star is that?
It's called Alcor. It's the last star in the Big Dipper's handle. It's right at the very end. Oh, there we go. No wonder it wasn't working. Okay. And now, let's do this. Let's bring up Alcor again. Well, that's not bad. It's pretty close. I'm going to do a little focus playing here, guys. That wasn't the focus.
Still buffering a little bit.
Is it? Alright. Okay, I'm going to change the speed now.
And I know it's not on this end because I have me running at 480p right now, just seeing if it was maybe on my end, but
okay.
It seems like it's buffing for everybody at the same time, so that's definitely encoder stuff.
All right. So we need to do something about that. Is it like badly buffering?
Yeah, it's like every 20 seconds or so.
Oh, that's disgusting.
So let me jump back in here in the studio.
Hash Brownie says, "Throw the wrench at the computer and it'll be fixed." Yeah, you know what? You're right.
Try going to 29.97 frames per second.
Okay.
That's actually a common one.
Yes, I don't think it lets me do that. It lets me do 29 or 30. It doesn't. That's the FPS I'm talking about.
Yeah.
I think you're talking about. Something.
No, I'm talking about frames per second. Common frames per second values. It should be. I have like 10, 20, 29, 30, 48, 59, 60.
In the video, or in broadcasting? Because in video.
In video, yeah.
Yeah, in video I don't have I have an FPS, which is frames per second, but it only goes in whole numbers.
Okay.
Yeah.
But you have a 29, correct?
I do.
Yeah, try that.
Now that's a little odd, but okay. Oh, you know what? Guess what?
What?
The 30 isn't applied until I start streaming again.
Oh.
So that means I have to stop the stream and start it. Now is that gonna?
Well, that's not hard. That's not hard.
No, but isn't that gonna like kick everybody out of the chat?
Nope. Nope.
Oh.
You stop it right away, and it'll say stopping stream, and once it clears and the start stream becomes available again.
All right. So now I'm streaming again, and yes, I can see the chat now. I've actually got I've got a chat over in the corner.
So now we are on 30 frames per second, correct?
Yeah.
Or 29, I should say.
Yeah, now we should be 30.
Or 30.
Because we weren't on
Yeah.
30 before. We never got to 30. I don't have a buffer health setting. Well, of course, in OBS, I mean, in the lower right corner, it's going between green and then it goes to orange and then it flashes red occasionally. So maybe that's what you're talking about, buffer health.
Yeah, that see, it's still giving me an option for 720 60 frames a second. It should be 720 30.
I'm doing 1920 by 1080.
Yeah, 1080p is still at 60 frames. I'm just telling you what the options are on YouTube.
Okay.
They're giving you a 1080 and a 720 at 60 frames a second, so.
Huh.
And it's still buffering.
For crying out loud. The audio isn't, of course, but no, everything else is.
Okay. Now I just refreshed it, and I'm waiting.
Wouldn't it be funny if we found out this is all your fault? All your problem?
Yeah, right. Yeah, right. All mine.
Yeah. I mean, just...
Well, put it this way: ever since I refreshed it, it hasn't buffered yet. Wait, and as soon as, well, okay, no, it's still going. So it's been about 25 seconds. It hasn't buffered at all.
All right.
So.
Well, I'm gonna just try to go to something.
And it just buffered. So you're looking
come
at a 30-second buffer.
All right.
Do you have an option on there that says downscale filter?
In the settings, let's see.
Above on video, above common frames per second values.
Let's see, under video. This is on the settings now. Under video, all I have is resolution 1920 by 1080, monitor 1. Aspect ratio 16:9. I have downscale, resolution downscale, yeah. And it says none right now.
Put on bicubic if you have that option. Bicubic sharpened scaling 16 samples.
I don't have that. Oh wait.
No.
Okay, so if I downscale, it basically I can drop it to like 1536 by 864. It's like 1:25. You talking about?
And that's underneath the downscale filter option?
Actually, no. The filter option is grayed out, and I can't get at it unless I think I have to select the downscale.
All right. What other tabs do you have besides video?
Well, I have audio.
Mm-hmm.
I have. Let's see. I have general. Let's see what's under general. Nothing. I have encoding, of course, which is I use X264, I use CBR, quality balance is at 8. I have a max bit rate of 6,000.
No, holy crap! Drop that thing down to 1800.
Serious?
Yes.
But I don't want to. No, all right, I'll try it.
Well, then we can go up from there. 1800 is the bottom level of HD.
Oh, okay. Then let's.
And then we'll go up from there if we. I mean, I run mine at 2000. So.
All right. Well, cool.
See what we got.
Let me go to. Should I just try 1800?
Yeah, go right to 1800 right away.
Okay, I'll do that.
And
we'll see what
apply.
we get. And I'll apply, and then of course I may have to start and stop the stream again. Maybe.
I don't think so. Usually you don't have to with the bit rate.
I don't. All right, so I just did that. So it's applied and it's doing its thing. So we'll see what happens, won't we?
I am going to F5 the stream just to see.
I thought when you said F, I was like, wait, don't do that.
And I'm just gonna count here. We're going good. It's not.
And you know what? I'm getting all greens on the bits per second down on the lower right at 30 frames per second.
Very good.
All right, I think we're out of the woods with that, and we
Let
can
me
adjust upward as necessary.
So we are on. I just want to be sure.
It's green. I got green, so I got good health. So I think that's it.
But we're still buffering.
What? How can I be? I got green.
Is anybody else buffering in the chat? You're all here to help us out to make this better for future streams as well.
Yeah. Actually, it doesn't matter whether I share my screen or not. It's what you see which matters.
Yeah, and Mark's on regular OBS, and I'm on OBS Studio, so that's kind of why we're reading each other, back and forth, what options we have. And right. On his, some things are named different than what they are on mine, even though they're the same program and whatnot.
Exactly.
But guess what? I'm gonna regret saying it. It hasn't buffered yet.
Yeah. Well,
for me since I refreshed it.
Stream health is green, so I think we're going to be in good shape. That's just me saying that. That's not truth speaking here.
Let's hope. Let's keep our fingers crossed. And then let's see, I got to work tomorrow. So maybe like tomorrow early evening, we'll work on the actual and get you in the OBS studio. And then I know I can help you out on that.
Awesome. Because when Bill was using it, it was working. And then it wasn't working, and he couldn't figure out why.
Yeah, well, now Bill's buffering.
That's funny. That's so funny. Not really. Okay, you know what I'm going to do now? Let's go see something. All right?
Let's do it.
I'm going to take us to another really cool place. I want to take us to the first double star ever found. All right? Ever. In the history of humankind, it was the first
double star ever found. Take us away.
The first double star ever found, and I think you'll appreciate it because it's right there in the Big Dipper, and it's really a cool star. And I will tell you in just a second. I'm looking it up in my database, and I'm going to tell a telescope to go to it, and we should be able to have a fairly good alignment.
Yep, and I will say to the people in the chat, the buffering issue, I have not experienced it since we reset this, so if you have, you might have to refresh a couple times just to get past that point and where he switched the frame rate, but besides that, it's been good. It's been locked on pretty good. And
make sure you go to the, make sure you click on the live button in there so that you get to the end of the stream in case you're not. So
that is a growing problem, isn't it? Sometimes it'll just stop it and kick you off live for some reason.
Yeah, and get to the current position. Okay. Here we go. We're gonna go to this star. All right, now let me just get my camera. Alright, that's the wrong value. We're going to dynamically change how it looks. And I'm going to change the ASA setting here. And I'm going to actually, for the heck of it, I'm going to take a picture. But not at 13 seconds, no way. I'll just take a 2 second picture. So here we go. Here's a 2 second shot. Alright. And boom. It comes up. And you see it.
Well, you got to remember, I'm about 20 seconds behind you, maybe, or something, from seeing it on YouTube.
You should see it right about now. It's about 10 seconds.
There we go, yep.
Okay, so about a full 10 seconds. Alright, that's not the object I'm looking for. Okay, I'm actually looking for something a little different, which I will tell you about. Just a sec. I see it. It's in there. It's just... Okay, 1 second.
It's a lot of blue-greens in that photo.
That's because we're looking at it at a very, very high... a very, very high setting. We're looking at it, incredibly high. And that blue is actually the moonlight that's bleeding into the image. So that's what you're seeing there. So that's unfortunate. That's a problem. But it is, unfortunately, what it is. So that we'll have to deal with right now. But I will be able to show you in a sec what I want you to see here. Hold on. Okay, I gotta set the speed. You know, the speed on the handset can be adjusted so that you can move the handset at different rates of speed. I just move the telescope at different rates of speed. Mm-hmm. And every time I go to find something, it actually has the telescope. It has the telescope set to different speeds, you know, and it'll set it to like it'll set it to a very fast speed or a very slow speed. It's not a bug. It thinks it's doing you a favor, and that's a problem, you know. All right, hold on. One more time. The other problem I have is that I've forgotten how much I dislike having bright light in the observatory dome.
Heard that. Hey, did you by chance happen to tell Bill that he might need a focal reducer for his camera?
I might have. I don't remember. I might have. Why? Did you?
I think he's I think he's having problems focusing the moon from what it looks like, especially when it's up close.
Oh, really?
And I don't think he has the distance to focus it.
Okay. All right. Now let me. I'm gonna come in close. This is the first double star ever seen. Okay, ever recorded. This is in the 1600s. This double star was actually found. It's actually called Mizar, and if you look in the tail of the Big Dipper, it's the middle star right at the bend. And Mizar,
which one are we looking at on screen here? Like, there's 3 points of light. Are they the stars or?
Yes, actually, the right-hand star is Mizar, and the upper left star is Alcor. It's called. That's a companion. The one down below, I believe, is a field star. Just one that happens to be in there. Now, what's interesting about Mizar and Alcor is that these two stars, they really were seen for the first time, and they needed a telescope. But when you go outside and look at the Big Dipper, you can look straight up and see these double stars just like this, just like that.
Now, these stars are close to one another, correct? They are within, by astronomical terms, super close.
I mean, to each other, you mean? To actually?
Yeah.
Well, actually, Mizar. This is the complication. Mizar is actually a star that's itself a double star. So we see Alcor and Mizar, and whereas Mizar. And
well, let's try that. Let's try that just for people that might not know. Define exactly what a double star is.
Yeah, actually, you know what? When I started the stream, what I wrote on Facebook, I actually talked about double stars in particular. But you're absolutely right. I probably should say that. Most stars are double stars, believe it or not, and it's uncommon or less common to have a star that doesn't have another star around it. Now, all the exoplanets we found around other stars. What's interesting about that is that all of those exoplanets happen to be, most of them actually, around stars that are singular. But that doesn't have to be that way. And we're seeing these two here, Mizar at the lower right and Alcor at the upper left. Now, as far as these stars, okay, the distance from us, okay, that Mizar is, along with the whole retinue of stars around it, is 85.8 light years. So it's actually, fairly close. The other interesting thing about the whole Big Dipper in general is that if you ever look outside, you notice how the Big Dipper is kind of a bright constellation. Everybody knows it. Well, there's a reason. The reason is because when the sun was born, it was born in a cluster like other stars are born, because a stellar nursery is a cloud of gas and dust from which stars are born. This particular cluster of stars that we were born in, some people believe, some scientists, some researchers believe, was actually what the Big Dipper is now. The Big Dipper stars were part of this original cluster that was our stellar nursery, and then they all migrated away from each other, because stars are all moving in space. They're going around the whole galaxy in an orbit themselves. It takes millions of years for a star to go around, galaxies, and even longer if they're big galaxies, shorter if they're small galaxies. Our stars are in our galaxy are actually fairly, it's a big galaxy comparatively. It's a moderate size. It's not the biggest. It's not the smallest. But this is the best thing is that we're looking here at this tremendous pair of stars so far, and I haven't told you about any more than just the two. But if we look at the main one, okay, the main one is basically kind of like the star Vega, right? It's an A-type star. We talked about different stellar types last night, but they go in terms of highest temperature to lowest, and from brightest to dimmest. The letter grades O, B, A, F, G, K, M. Now, that when I was getting my degree in astronomy, we were taught, and this is how far we've come, we were taught to remember that by saying and memorizing, "Oh, be a fine girl, kiss me."
And oh my!
For the girl astronomers, they would say, "Oh, be a fine guy, kiss me." And I cringe now thinking about the fact that I actually did memorize that, but that is what it was, at the time. So, the interesting thing is that we're seeing Mizar and Alcor as double stars. Mizar itself is a double star. Alcor itself is a double star. And so we're actually seeing two double stars here, and they're all revolving around each other. Alcor has a tiny little component circling it. Alcor is the one at the upper left, remember. Mizar has one around it, and it's the one at the lower right. And let's see if we can actually, let me just do something. Let me see if I can get closer a little bit. And
now, is this your special invention you're using to get these images?
I mean my extra special stellar dealie? Yeah, that's it. Okay. And you can see right now I have it set so that the stars are just a little bit brighter, but I'm actually going to get a little bit closer to Mizar here so you can see. We're only looking at one now, but there's Mizar. Notice how Mizar is more than one star, right? And I'm going to come out just enough I'm going to pop out a little bit to change this the graphics settings just a little, because I want to actually be able to make the exposure a little bit less bright.
Amazing. And these two stars are like close enough to be pulling on one another?
In fact, they are. Okay. Well, first of all, in terms of Mizar's, in Mizar's case, okay, that's a little better now. So now you see Mizar and Alcor. Now, I showed you a trick yesterday, which I'll repeat. In order to make these stars, show you their color, because it's hard for stars to show you their color. You can't really tell what the color is, can you? But you can. No. You can if I do this. Okay. This is I've changed. I've defocused the stars. All right. And of course, Mizar, the main component of Mizar, all right, is the brightest, and you see it, and you see that the color is kind of like a blue, and that's exactly what Mizar is. It's sort of a bluish white. Now.
And what gives off bluish light?
The star itself, okay, it has a bluish white light that it gives off, and that has to do with its spectral type, its spectral class, the type of star it is. So an A-type star like this one will give off kind of a bluish white light. B-type stars just before, remember the O, B, A, F, G, K, M. Okay, the B-type stars just before these A's will also give off a blue light. So we're actually looking at a blue light that's being given off by Mizar, a bluish.
Now, do you know offhand how far away this double star is to us?
Yeah, it's 85.8 light years away from us.
So we're looking at 85-year-old light.
85.8-year-old light. You're absolutely right. Yeah. But you're right. You're absolutely right. And I think that's an interesting thing to discuss with people when they look at stuff like this and they say, well, that's not that far away, right? 85 light years.
It's a form of time travel.
We are. We're looking back in time, aren't we?
Yep.
We are actually looking back in time, and we're seeing Mizar as it was almost 86 years ago. Now, also keep in mind that these stars that we're looking at right here do orbit each other, you know, and that's pretty cool. And now all of the stars in the Mizar system, which we have to call it because, you know, it is a system of more than one star. All of the stars in that system are normal hydrogen burning stars, meaning they're burning hydrogen into helium the way our sun is. That means that they're called type 5 for what's called a luminosity class. So the actual stellar type would be something like an A5, okay, A and then a number for like where it is, you know, and then 5. And that's a Roman numeral V, you know, 5.
Well, with your camera, how close can you get to those stars?
Well, with the camera, that's it. You know, I can't get any closer. I get a couple of good chunks of you know, distance that I can go. And the nice thing is, the camera was designed to do this, not to zoom in on stars. I'm using it that because it's my special handy dandy, you know, ultra special top secret zooming technique. It's actually used to. It's actually used to focus. All right. Because when you zoom in and focus, and then zoom out with a lens, you actually achieve better focus. When you zoom all the way in, focus on something really small.
And it is possible, I mean, if you're out of focus, that you could possibly see something that resembles a spaceship, but it just might be a satellite or a star.
That's correct. And you know what? You should all keep your eyes peeled because, especially when we come out to this wider view, okay, you might see a satellite go through the field. I saw 2 the other night, and that's just what happens. So I think you should look for that.
We had a couple as well the other night. Actually, I just posted one of them to the channel today. That one, that's the slow mover one, which really, yeah. I was trying to think. I was looking up the data, satellite data, to find out which one would have been in the area in Miami from his view.
Yeah. And
I didn't find any close ones, but I did find a what was it? Well, it was too blurry, I think, to be the LR or the LROC thing, right?
Well, LROC is circling the moon, isn't it?
Yeah.
I mean, that's
and you didn't see a shadow or anything, so.
No, you're not going to see that because that would be 240,000 miles away. You're seeing something superimposed on the image of the moon that's in Earth orbit. But, you know, when you see satellites go through, you were used to seeing them go by faster. So you go, wow, why is this one going so slow? Well, the reason it's going slow is because it's actually in a higher orbit. And the higher in the orbit you go, the slower it can go. I mean, at 252 miles, the ISS height, your speed is about 17,500 miles an hour. But when you get out to geostationary, okay, that speed can drop. That speed drops to just a couple thousand miles an hour. Now, the Earth is rotating at about 1,000 miles an hour, okay? So at geostationary orbit, you know, satellites are going to rotate or orbit at about that speed, all right? And that's not magic. That's actually how far out you have to go so that your orbital speed can drop to the rotation rate of the Earth. So, you know, that magic number is something that we just discovered. Well, you know, how far do you have to go? Where do we have to send our satellites so that they will actually orbit at exactly the rate that the Earth's rotating, so they sit over the same spot roughly on the Earth at any one time. And that's called geosync or geostationary orbit.
Well, I was thinking as soon as I saw it and I saw it moving, I knew it had to be out there pretty good. You know, my first thing was like, you know, I mean, you got to figure, I mean, low Earth orbit or geostationary orbit is where the bulk of your satellites are. And then you get, you know, into your higher Earth orbit where you have a lot of science satellites, especially U.S. I mean, there's a lot of them around there. But I got to thinking about, like, the European Space Agency that launched on the Soyuz and whatnot that are out about 100,000 kilometers, you know what I mean?
Yeah.
So...
Taking an image, just so you know.
Well, yeah, I mean, the European Space Agency is the bulk of your 100,000 kilometer, you know, orbits. You know, I think we only have maybe 2 out that way, and then the rest of them are from Europe. Pretty much everybody. I mean, we're using the same, you know, pretty much the same in sharing. But
exactly so. I mean, if someone wants to do geostationary, then whether it's ESA or you know NASA, it doesn't matter. You know, they're going to do it. So I'm pretty sure that you know that the cooperative ventures are, you know, pretty pretty clear about this. You know, they don't have any issues, and they're willing to share the space. There's no issues.
Yeah, and I'm looking at 4 satellites alone that are at the 70,000 kilometer, and they're all space science that were launched on the Atlas V.
Oh, sure.
At 70,000 kilometers. So yeah, there's a good chance it might be one of those. I don't think it was one in geostationary just because of the speed of it, and we have seen satellites that were in geostationary that go by a little bit quicker.
Right.
So I'm thinking it's one of those further ones out, whether it be, you know, the communication satellite from, like, because I think SiriusXM has one that's out there at about 45,000 kilometers or so.
Yep.
So there's possibilities, and that's usually where Sirius puts theirs. They put theirs between 40,000 and 50,000 kilometers. So.
Yeah, and you know, I think that what people, you know, what people like to see and understand is that when you're doing these kinds of streams, you might see an object that looks like a star, but then when you take a photograph of the sky and say you do a longer exposure, like, you know, or you actually let it drift. You turn off your clock drive, that is the drive that follows the stars, because see, we actually have a clock drive that's following our stars right now, because this is a magnified view. And it's not budging. It's not going anywhere because we are locked on, and we've got very good alignment. So we actually can see that the clock drive, that is, that follows the clock of the Earth, you know, the rotation rate, is right on. So, you know, when we do that, if you were to turn that off, then all the stars would start making a trail because the Earth is going to rotate out from underneath those stars. However, if you do that with a wide camera on, you know, a wide view, and you do it along the celestial equator, you'll see something odd. You'll see streaks for the stars, but then you're going to see bright spots every so often. Guess what those bright spots are? Those bright spots are the geostationary satellites because they're going with you. They're orbiting with you. So they look like other stars when in fact, and they look like they're moving, but they're not. They're actually they're moving at their orbit, which is the orbit rate of the Earth, and so it looks kind of cool, and that's really neat.
And the bulk of geostationary orbits are communication satellites. I mean, that's the ones that they need the most to be stationary.
That's right.
Just the info for anybody that cares. But then you have thousands of them in low Earth orbit.
Yeah, that's true, and some of them come down. You know, that's another problem. You know.
Yeah.
But. So I'm gonna, this is just wanted to show you. This is the first double star ever found, and it was found in the 1600s. And it's really a nice sight you can see with your eyes. But then with a telescope, you get to see that other component down there. You know, when I zoomed in before, you saw it. You know,
and believe it or not, this is the first time I've actually seen it through a telescope.
Well, how about that? That's
so.
Cool.
Thank you.
Yeah. So we're filling it up. So here's the view I wanted you to see. The whole stream now is showing Mizar on the above on the bottom right. Okay, its component down below, and then Alcor, the other component that's orbiting Mizar, way on the outside. And see, these stars are gravitationally bound to each other, and it seems like, how can that be? Well, they are 85 light years away. So at that distance, that puts Alcor at a distance that's such that it can actually be gravitationally bound to Mizar with no problem. And that's what's kind of cool. I like that a lot. So I'm going to try and find something else, even though the moon is up right now. I really do want to try and find this if I can do it, because I want you to see this if I can get it. If I can't get it, it has to do, not with me, okay, it has to do with the fact that the brightness of the moon kind of precludes it. So now we're moving.
Well, once again, welcome to everybody in the chat that decided to come into the SkyTour LiveStream with Mark D'Antonio.
And you.
Sitting here hanging out, and we just checked out a double star, and now we're moving to a surprise.
A surprise, right? It's a surprise, man. All right, now what we're going to do is we're going to just take a test shot, because this is what you do in astronomy. You take test photos, all right, and you see whether you're actually going to have what you want in the view. And so we're going to look and see. You can see there's a couple stars in there. All right, but I'm going to actually do a 1.3 second exposure at 51,200 ASA. All right, and you'll notice actually, and I'll bring that back. Okay, so there it is. That's a direct shot. We just took that. That's a live shot. Now, I'm not seeing what I was looking for in particular, but that's okay because it may actually not be there. I might have to move it a little bit, but I'm also suffering from the fact that I've got this bright glare in my observatory because I've got the chat over on the left side, and I've got the stream over on the right. I just adjusted the sizes to make it a little less obtrusive.
You know, you can switch to night mode.
How do you do that?
If you go to you have to be on a normal YouTube page, but once you go to night mode, it blacks everything out, and then you can pop out the chat, and it'll be black background.
Oh, see, I like that idea. Okay, well, then what? Next time we do that, we're going to do that.
Yep.
All right, so right now what I'm going to do is I'm going to just try and find this object. Again, if you saw the gyrations I was going through right now, the angles I was leaning and everything is like crazy. That's like... I might as well be trying to do this from inside of a mall parking lot. It's so bright in here.
Guy's a master.
Yeah, well, it doesn't matter how good you are,
And don't be trying to go and ripping them off and stealing his ideas, Mark, because I know that's what you're thinking. I was told on good authority that's what you're doing.
Oh yeah, that's me. Yeah, well, I'm pretty sure that people are wise to who's trying to do the best for people out there, and they know that you and I, for instance, we don't play those types of games.
Yeah,
some do.
And we don't take part in hearsay and gossip.
No way. We do not. Okay, I'm going to change the speed a little bit. I'm going to go 100.
And just remember, everybody, space is for everyone. So no matter who you are, what you're doing, if you have a pair of binoculars or a high-powered set of glasses or a telescope or whatever, point it up. Point it up and show the world.
All right, I went to full screen mode so that it's dark in here now. And I'm doing that because I want to be able... That's not a star, that's the mouse cursor. You'll see that in a second.
Oh my.
Oh my. So what I'm trying to do is locate one object in particular. And again, unfortunately without a moon, it would be so much easier.
And while you're doing that, I'd like to congratulate Fantasy Ecstasy in the chat, who is going to get married this weekend.
What?
Yeah.
Wow.
What's wrong with you? Don't you know marriage is a penalty for shoplifting in some states?
Holy cow.
Just kidding.
I can't believe you said that.
Many happy blessings to you.
Wow. Fantastic. How did you find out about that?
Well, I seen it in the chat. He was talking about it, and then Amanda messaged me and let me know for sure.
Okay. So she said, make sure you say something.
Yeah, Amanda put the smack down on me.
Yeah, well, I
was going to congratulate him anyway, but that's okay.
Fantastic.
And welcome to Paul. Paul is hanging out in the chat as well.
Yes, he's out there? Nice.
Yep, he's got rain down there, so...
Oh, well, I'm glad he's here. Thanks for coming, Paul. Let's take a test shot here. I'm going to go to...
Yeah, test shot away, and I'll welcome, I'll just go down the list. Amanda and Fantasy and Paul and Dapple Ben and Rockstar and Genghis and Heidi. Heidi's around and Sherry's around and am I missing anybody?
Genghis Khan.
Genghis Khan. Yeah, so welcome everybody. Thanks for joining us. I'm just here hanging out with Mark, bringing his channel ratings down a little bit.
Yeah, well, it could be worse. There could be strange noises.
Yeah, we're just working on stuff, making sure Mark's doing what he's supposed to. I got to make sure he's not part of the Illuminati or anything.
Well, not anymore. I gave up on that, actually.
Yeah. I kind of figured you did.
Yeah. But all right, so this object doesn't want to show itself tonight because the moon is kind of bright. But you know what? I always do that too. I have a different plan every time, and then I say, well, I won't do this, I'll do that. And then I end up doing this anyway, when I should have done that. Mm-hmm. I know that makes sense. So I'm going to look up just another thing here just to show you. Because there's a couple things that I think are really cool that I'd like you to see. Of course, it'll take me a second here to locate them. Indeed. You alright over there, Keith? What's going on?
I'm fine. I thought that was you.
No, that's not me.
Well, it wasn't me.
Yeah, my microphone is over on the desk over there in this observatory. It's not near me.
I'm trying to blow in the microphone now to see if it.
No, it wasn't that.
No, I thought it was you.
That's not me.
I have no idea. That maybe we're haunted.
Yeah, I was like, what is he doing? That's ridiculous. What's he doing?
Hey, we just had a guy named Mad Flatter in the chat. Congratulations, you are the first ding dong of the night.
Mad Flatter? Oh, that's great.
Yeah.
Isn't that nice? Isn't that something? Mad Flatter. That's interesting. I'm trying to locate it.
That's okay, Mad Flatter. We love you tomorrow, okay?
Exactly. Alright, I'm gonna do this. Go there. Let's do that. Okay.
Sounds like you're about to launch a jet.
I know, right?
Holy crap.
Yeah, that's just the thing, you know, it just makes this noise. Makes the noise, what can I tell you? It's like, okay, getting parameters. getting flight parameters.
I'm sorry, I cannot do that, Mark.
I'm sorry, Dave. I'm afraid I can't do that. Yeah. So this was I'm just taking, it was a shot actually of a star field. Now, unfortunately, with a bright moon.
That's going to be tough.
Yeah, well, for this, you know, I have to, you know, I can make adjustments to it, but, you know, well, that's the other video you're not supposed to see. No, I'm just kidding. I'm trying to figure out a way to actually make this a little bit better. I could just pull that up a little. There we go. Okay. Now, let me see over here. Oh man, I can see that moon glow. That's beautiful. I really should I should point at the moon since no one's looking at the moon right now. No. I'm still waiting for it.
Yeah, I don't understand why you don't, man. I mean, go for it. Absolutely.
Well, it's just, you know, the moon was your thing, you know.
No, dude. This is a collaborative effort between everybody. Now, you're seeing right now that Paul is clouded out and rained out in Miami, and guess who's online? You and Bill, who have clear skies. Go for it, man. Get it done.
Exactly. Okay, so.
And if anybody wants to know what me and Mark are kind of under our breath joking about, we actually had somebody today actually try to pit P and K against Mark and Mark against P and K. That's why we're, you know, making some comments that we are, because we found it just hilarious that they were trying to, you know, pit us against one another when we were talking.
As if that was
the thing behind that. So if you hear us making smart ass comments, you'll know why.
Yeah, as if it would be successful, because we're certainly not. You're not going to do anything that it jeopardizes what we do together. This is crazy.
Yeah.
You know?
Yeah. And specific, they were trying to pit Paul against Mark. You know, like Paul's better at what he was doing. And it was just so crazy. And me and Mark were on on Skype? I think we were talking about it. Yeah. And we were like, this is nuts. Like, what are they doing?
Yeah.
But
exactly.
You know,
it's absolutely nuts.
I don't know. So now you all know.
Look, it's P&K Space Watch.
Yeah.
Hold on, I gotta focus a little. Okay, here we go. Okay. That's
beautiful.
What it'll be. So that'll be in just a couple of seconds.
Oh yeah, Mark, and another thing is you're in cahoots with Hollywood.
Oh, well.
To steal ideas.
Oh, really?
Yeah.
Well, I guess that's something that people will say, I guess, but it's certainly not true. I'm not in cahoots with anybody. But hey, you can't convince some people of these things. Sometimes they just believe what they believe.
Yeah.
And there's nothing that you can do about it. I wonder if some of the folks remember what I did yesterday. I actually came over to the edge of the moon, and I actually changed the settings on the camera, and you can actually see the unlit side. I could do that again, actually. I have to go back to this view right here.
That's gorgeous.
It is, isn't it pretty?
I like the clarity. Like, it's almost like you have a little bit more edge definition than what Paul can get.
I don't know. I think that I got a 10-inch instrument, and he's got an 11, right? He's got the 11.
I think most of the time he uses the 10. If I'm not, Paul's in the chat. He could answer the question for you. I'll let you know when it comes up. But I'm thinking most of the time he uses 10. I think he busts out the 11 when he's doing something like, because I know he did it one time for the nebula and whatnot. He just gets that extra little bit of light input definitely helps. But I think he uses the 10 most times.
Now, aside from the glare here, you can actually see.
That's gorgeous.
You can actually see. You can actually see it. You can actually see the other side, the unlit side of the moon. I won't say dark side because it's not. It's just the side that's unlit. You can see it. You can see the curve right there, just at the right side. And I know that's not very useful to people, but you can see how much you have to overexpose. This brings up a good point. You see how bright that is? Okay, we have to overexpose the moon tremendously just to see the Earth-lit side of the moon. Okay, which we can actually just barely see there in its curves. It goes down around the lower right section there and curves up. So you can see the separation between black and gray. Well, that gray is actually the surface of the moon as seen here, through this telescope. But, when astronauts are on the moon, for them to actually shoot the moon right, okay, they couldn't take pictures like this because pictures like you're about to see, okay, this is not good. Okay, they have to be able to have pictures that show something. So what they do is they stop the camera down, they use a different film, and they use the settings to make it look like this, what you're about to see. And stopping down the settings and making it look like this precludes you from being able to see things like stars in the sky, all right? Because the moon, all right, doesn't have very high reflectivity, believe it or not. However, it does reflect about, 13 or 18% of the light that hits it, but that's more than enough to cause the overexposure because we're seeing it here, So we actually, we can actually turn this even lower, but I'm actually going to take a picture here because that seemed kind of pretty.
That is crispy.
And you'll see there's the picture. So I'm going to actually stop it down a little more.
Actually, I'd probably take it down just a couple more notches.
I did. So now we got that. That's pretty, don't you think?
Yeah.
So
looks like a poster.
Yeah, this is the moon that we just took a picture of, and now we can actually zoom in, as much as we dare, because now we actually can, go in,
Let's do it.
See that? So that's what we just took a picture of.
Let's see how the atmosphere is behaving above Connecticut tonight.
Well, for that we actually have to. Let's see. Now, right now, the atmosphere is pretty still. When I actually did it the other night, we could overexpose it just a little bit when I brought it over to the right, like this. Well, the moon to the left, the telescope to the right. Okay. When I did this, and it's going to be going out of the view a little bit, yes. And then actually, when I increased the sensitivity of the camera, here's what you see.
Can you send me that picture on Facebook tomorrow or something?
Of course I can. you have pictures like this.
Yeah, I know, but I want that one. Thank you.
But now, if you look, okay, here's the moon right up. Now, here's something you do in astronomy. You want to figure out how your optical system is performing. You do what I'm doing right here, and you see it right about now. You should see the moon is now moved off, and you just have a glow. Okay, this gives you an idea of how your optical system is working, whether you've got dew on the lenses or whether there's clouds up there. Right now, this is a live shot, so we actually don't see any movement. If we saw movement, then there would be light clouds going through that you don't see. We don't have that. So we know that we're good for the clouds. what we do see, we have some hazing, and that could be internal reflections because the moon is really very bright, and that could be causing us problems. Now, the next thing is, if I'm going to bring this back, I'm just going to increase the speed a little bit because we don't need to take so much time coming back. All right, it's so bright. Okay, my whole observatory just went bright white.
No idea, because we're 30 seconds behind.
Well, you're I'm saving you the horror. Okay. Yeah. See, now you see it though, don't you? It's about 10 seconds, isn't it? It's not 30.
It's probably about 30.
Is it really?
Yeah.
Well, yesterday it was 10. How come?
Oh, sometimes it's like that. I mean, we get some nights where it's only like 10 seconds too. It's just, I mean, we just pretty much know now the base is 30 seconds and we go from there.
Well, you know what? I want to thank you, Keith, from P&K Space Imaging. Go see them every night when they're streaming when it's clear.
Heyo!
I want to thank you because with your help, you know, I think we've tuned the streaming parameters such that now I won't have any buffering issues anymore.
Yeah, we'll do a little bit more tweaking just to make sure we get it right. But yeah, this is definitely a lot better. I mean, it still buffers every now and then for like a second real quick, but we definitely want to get that out of there totally.
Yeah.
So
I agree with that. I think that's cool. So I'm just going to zoom in one more time here because I want to actually see what I've got. You know what this tells you, by the way? When you see it like this is showing you, this is how, now you see the moon's drifting?
Mm-hmm.
Now look at it stops. Okay, that right there that you saw, that is called backlash. That's something with the drive system on every telescope. When you find an object, okay, if you move an object, you go to an object and you stop, all right, if you're moving to the left or the right, all right, then the telescope has to have, see, there it goes. You'll see it in a second. It's getting in a little while. It drifts around, and when it does this drifting, that's the drivetrain catching up, and it moves very, very slowly. And so what you're actually seeing is the actual drift of the moon in the sky if you had no drive. And then it catches up, locks on, and continues to follow. Do you follow? You see what I mean? Mm-hmm. And that's what this is doing. So you know, you learn about these things, and this particular telescope has a huge number of capabilities. It has the capability to do something called periodic error correction. It has the ability to actually change the look and feel of the drive. You can train the drives to actually work and operate the way you want them to, and it's really cool. You know, so now we're back. Okay, cool.
Hey, it happens.
Yeah, you'll see. You may see a gap, or I don't know how that works. You might see a white screen because that's all look like a supernova.
Yeah, it might buffer for a little bit, and then it'll kick back on. Yeah, it already did. You're good.
Okay. So what I'll show you here is when we look at this moon here, just to give you an idea. You see how the gray areas, obviously, those are Maria. Those are what they used to call seas, because in the earlier days, you know, they didn't know that there wasn't an atmosphere. They thought that these were seas, and they were seeing another world. Obviously, we've come a long way, but the canals on Mars were the next debacle that we had. We had people talking about canali on Mars. You know, Schiaparelli, he was talking about canali on Mars. And when I did a NASA's Unexplained File episode on Mars, we talked about the canali, and we talked about the fact that they ended up being nothing like what Schiaparelli thought in real life when he finally got there. But, you know, the interesting thing about the moon seas, so to speak, is those are all dust. That's actually soft dust. That's pulverized dust. So when you actually go to the moon and you go to the lunar highlands, which are down below there, you see where the mountainous ranges, that all the shadows we can see are, of course, around the highlands. And you go to the moon and you look at this stuff, and then you realize, wow, the moon is literally covered everywhere, even on what looks like sharp-edged craters, okay? And we zoom in on a crater, let me see here. If we zoom in on a crater, and we get to one spot, for instance, where we think that maybe there's an actual, like here, for instance, we go and we look at this and say, hey, those craters that we see inside that circular basin there, those are called basins, those large black areas that are filled with the dark gray. We see the craters in there. It looks like those are hard-edged things, and that the mountains are hard-edged. They aren't. The moon, in fact, if you stepped on them, you leave a footprint because you're seeing a surface coating of many feet of dust in some areas. The craters, some of the craters, if they're simple craters like I've talked about on Keith's stream or P&K Space Imaging before, the bottoms of these craters are round. But some of them aren't round. You can see that they're actually filled with a little bit of dust. That's not, in that case, with a complex crater, it actually just popped a hole in the moon when it hit, this object hit. An asteroid or whatever hits the moon, leaves a little indentation. It doesn't go deep enough to actually cause lava flow. Like, it doesn't fracture the deep inside of the moon so that lava comes bubbling out. That's happened everywhere else that we see these dark areas. These dark areas on the moon are Maria that we've talked about. These are actually lava seas, and these flooded out. Now, here in the center of this frame, you'll see in a couple seconds, you're going to see a round gray area. Well, this round gray area was the site of a large impact, and when you finally see it, you can tell this used to be a giant crater when it first formed. Then it was filled with lava. Then it was filled with pulverized dust from other impacts. So I don't know if you see that now, Keith. It came up by now, right?
Yeah.
It's in the center, right?
Yep.
But now if we go back to the left side, okay, and as we move to the left, just to the left of that, you see, ringed by fairly high mountains, you see another bigger impact basin that occurred on the moon. And that impact basin is very much older than the craters that are within it. All right? So when we look at this, we see an impact basin, and then that impact basin was from an impact of an object that actually caused a fracturing deep inside the moon. And then the resulting volcanic action, the lava that came out of the moon, it was molten at the time inside, that flooded that area and filled it in. Then later on, maybe perhaps billions of years later, a couple billion years later, then those other craters you see inside that impact basin hit, and then the same process applies to them if they went deep enough to cause some type of internal damage that caused fracturing deep underground to bring up lava. Mm-hmm. It's really neat, and the moon has its own history to tell. But the one thing that's basic is when you see those Maria, all right, on the moon, and I know I'm skipping kind of around them, and that's fine. When you see those Maria on the moon, the thing to remember is that craters that you see on the Maria are younger than the Maria themselves. They're actually more recent because the Maria were actually, nice flat gray areas of lava, and then they were overfilled by debris from other impacts farther downrange or elsewhere, and then they were hit by other objects that made new craters. Also, back on this central Maria that we see here, and they'll show up in a second, you actually see a faint ray going kind of vertically through the center of it. Now, a ray is from what's called ejecta, and ejecta is the resulting splash, basically, of an object hitting the moon and spraying out stuff. And I actually I used to do, when I taught, I actually used, in the university, I actually used a big vat of white baby powder and gray powder, and I put them in a gigantic bin and had the students drop big weights in them. And the top layer was white baby powder, the top layer was gray powder, and underneath that was all baby powder, so it was white and gray. When they dropped this thing inside, what happened when they dropped this big ball bearing down inside this vat, you saw that it would hit and go sploosh, it would make a poof. And then when the dust cleared, which settled everywhere else and put a fine dust all over everything else, when that dust cleared, you saw this ray structure. The dark stuff that was underneath came out and went flying out over everything and made these radial rays, like you see a little bit here, radiating out. Mm-hmm. Now, you can tell from in this image, you can tell that these ray systems come from a crater that's farther north than that crater in the middle, that little tiny crater. It's not coming from there. So what you do is you follow the rays, and it tells you where the crater is. And in this one, are you able to see the source crater? I can see it, and I'll move it, and I'm gonna center it right in the view. The source crater for this particular set of rays is right about there in the middle of the view. I don't know if you can see.
Mark, let me ask you, what are your thoughts on some of these things that people say they find in craters, like whether it be spaceships or buildings, or have you ever seen any photos that kind of took you by surprise and said, really, is that, and it actually made you kind of do a double take?
When I did a TV special called Aliens on the Moon, and I was one of the guys consulted, but the way they played it up as I was going to be the guy that gave them all the answers they needed, because they gathered all this info, then they brought it to me, and I was either going to shoot it down or I was going to...
I remember that. They were doing a whole episode.
And all they got from me, I actually, for that particular show, they wanted me to do an awful lot, so I did an awful lot. I actually created a replica lunar soil based on the scientific properties of lunar soil. That was me touching the camera when you see it bounce a little. And it mimicked all the static charge properties, it mimicked some of the chemical constituents, and it mimicked the clumping properties, and it mimicked the fine feel. The only thing that I didn't mimic, because it was dangerous, was to mimic the glassy particle nature of the material. I couldn't do that because I didn't want anyone helping me do this get silicosis and die. Okay, kind of a big one there. It's sort of important. But I did that, and I used that to show them how certain features on the moon were what I believe to be simply illusions. And I showed because of the angle of the light. Right now, we don't have any in this particular image. We don't have any light that is really low angle. We do when we get near the terminator, which is the part to the left. Right. And I'm going down right now, but I want you to see that that ray that I was talking about before, it's more pronounced now, and it's right there, kind of in the center of the view when this comes up, and you're going to see it. And that ray comes from a crater that's up here, and I gotta put it right in there. Okay, it's hard to stick it in there. There we go. All right. So it's that crater that you'll see in the center of the view, a little crater, is what made that long ray. And you have to say, well, why is that? Well, the answer is because it doesn't matter how big the impactor is. It matters how fast it's moving, and it matters how it hits the moon. Rays are formed a lot of times by objects that actually strike the moon straight down. So what they would say would be like an angle that's perpendicular, to the surface of the moon, a normal line sticking out of the moon. It goes right down that line. If it's on an angle, then you sometimes see rays, like with the craters Mizar and Pickering on the moon. You actually see. Okay, sorry, I got I'm in Hicksville.
I was gonna say, what, you got a parade going on up there?
No, it's sort of Hicksville, so I kind of have these big diesel pickup trucks going by all the time with the.
Oh, not me.
Yeah. Oh yeah, you have one of those big dualies. You needed it to carry back that thing. So, but the point is, like with Mizar and Pickering on the moon, these two craters, one of those craters has a strange ray structure that you see, and it's like a streak that comes out directly from the side. That's because the impact was on a glancing blow. It came from the opposite end, and when it hit, it splashed the stuff out ahead of where it hit, and so you can actually see the anatomy of how a meteor or an asteroid hits the moon by looking at this, and this is just fascinating. And believe me, I've been looking, by the way, for other things like satellites and stuff going by. I haven't seen them yet, but. That'd be cool if we could see the ISS pass in front of the moon tonight. One of us
has got to capture that thing crossing the moon face. That would be absolutely awesome.
Yeah, I know that I saw some photos taken by a very special NASA camera, and it actually showed the exact shape of the ISS in front of the moon.
Nice.
And it was beautiful because it was just stunning. And I thought, wow, that.
Paul has caught planes. Where we've taken a lot of still images. I mean, that's happened 3 or 4 times since I've been working with him, and just even those silhouetted against the moon are gorgeous. I can only imagine what the ISS is going to look like.
Yeah. Well, the thing is, you get an interesting effect because telephotos operate strangely, and when you're under telephoto power, the ISS can be made to look like it's so much more massive than it is. And telephotos have that weird property where the things that are closer to you look bigger, of course, but things that are farther away don't have the same impact on you that things closer to you have. And you get this odd scale illusion with telephotos, and it has to do with compression of the image and compression of the way the image looks to you. I have to show you to see it. But I was talking about low-angled light. Okay, here's coming up. You'll see an example here. This is an example when it comes up, a crater that's just now getting just a little bit of light in it, and this crater, I'm going to actually increase and then come back. I'll zoom back out and then come back in. I'm going to kind of just make it a little brighter. And I'll pop back in now. Okay. So now we look at this crater, and you'll see it momentarily. It'll zoom out and then come back in. When you look at this crater, you actually see that it's got this low-angled light to it. And for the aliens on the moon show that I was talking about before, we looked at, I was showing things like, not like this particular, but the same kind of thing, where they saw black in there and they thought that rim lit on the left was like a lunar bridge, in the air.
Is that the one they were talking about that they saw?
Not this one, but I'm using it as an example.
Okay.
And what it really was two ridges next to each other, and the center between the two ridges was dark. The two ridges were lit on top because the sun was at a low angle, low enough to light the two ridges, but not low enough, or not high enough actually, to fill in between. And with the high contrast film they were using, that they had to use, that they only had at the time, for those beautiful Hasselblad cameras they used, it looked very much like you're looking at this giant lunar bridge. And I was like, oh no, actually those are just two ridges, side by side, and I can show them to you. And I created it. I showed them that. I got a light from the studio that I work with, and I put the light on this ridge and showed them exactly what this was. Yes.
And you know what's crazy? With that program, they did everything they could to make it look like it was what they were talking about, like with them highlighting the area, and just they did everything they could, so you had no choice but to see it.
Yeah, and that was part of their plan. And I told them ahead of time. I said, if you're gonna try and make me be one of these people that just signs on to everything you say, and they wouldn't even let me finish the sentence when I talked to Bob Kiviat, who was the producer. He said, "Oh no, we want you to tell us exactly what it is. We want you to tell us the truth." Okay. And he goes, yeah, because you're the guy. I mean, you're the guy that knows. So we want you to tell us what it is. Okay, I'll give you my opinion. I can't tell you exactly what things are because I may not know. But I will give you my best shot. Okay.
That's one thing. Like that show, and even some other astronomers, whatnot, they can't take criticism when you tell them. What they're looking at isn't exactly what they think it is, and you show them some kind of proof or some kind of option of what it might be. Yes. They just, it doesn't matter. They just want it to be what they think it is.
And it makes their heads blow up. They can't handle it. I'm doing a little focus thing here. All right, that's pretty good. I'm getting some good granularity here. All right, so that. When you see this come up, I'm centering on this little crater. What's interesting is you see this crater has this debris around it. And it's really, I like craters like this because they tell us a lot about the conditions at the time when this crater was formed. The moon was in flux, there was a lot going on, and it's sitting in a highland area above the surrounding Maria. So the Maria is all around it actually. And then you have this little area of highlands that were left. You can see to the upper left more with a mountain ridge near another basin that we saw earlier, which is filled in. And you see that little highland that this crater is punched into. That's precisely the kind of thing that that type of thing gives us a lot of information, because that tells us something about when the Highlands were made versus when that crater was made, and it tells us something in addition about, and if we see rays from that crater that go out over the Maria, you see we actually can build a chronology of what happened on the moon when. So we know that these impacts didn't all fall at the same time. They didn't happen all at the same time. It happened over 1 billion years. And you can actually look at the moon and go through chronologically and say, okay, this happened now, and then this happened after, this was before that, and you can literally go over the moon and pick apart all the things you see, all the features, and kind of have a rough idea of when they actually occurred. I mean, that's...
And it's kind of amazing, too, how they do that without actually being there.
Yeah.
You know what I mean?
Yeah. Well, we couldn't have done it without going there with probes, and it was. I thought it was so pivotal when one of the astronauts on one of the Apollo missions, he's walking around on the moon, and next thing you know, I'm seeing Surveyor, which was sent up there, earlier in the '60s. And made a soft landing on the moon, and there it was, an astronaut standing there touching a space probe that was giving us the latest information we ever knew about the moon, years and years before he arrived. And now we had a human person standing there with the old technology, and he was actually there touching the probe that came from the Earth, a decade earlier. That was cool. You gotta look for that picture of Surveyor with the astronauts. That's just such a neat thing. Yeah. But anyway,
actually, you know what, Mark? Do you want me to bring in anybody with you? Because unfortunately, I'm going to have to go here. It is 20 to 11, and my butt needs to be up at 4:15.
Well, I was thinking about doing this as a relatively short stream, but I'm thinking we're going to continue a little longer. You can, I don't know who's in right now. I don't know what Bill's doing. If he wants to come in, he can come in.
I think he's still doing his stream, if I'm not mistaken. But I can bring pretty much anybody in you want. You want Amanda? Or
bring in Amanda. That'd be fun.
All right, let me see if I can get her. Amanda, are you available? Just let me know in the chat, and I'll...
She can actually give me some chat questions, because I haven't been able to see the chat since I got in here. I went full screen on this. I'm actually gonna jump over to Jupiter right now. So.
Yeah, let's check out Jupes before I go.
Okay, and moving. Yeah, wow, look at that. It's so pretty. I'm just kidding. It's so close to there. It's amazing. It'll be in just a second. Gotta change my speed a bit.
I don't think it'll allow me to add her because she's on Do Not Disturb.
Oh, really? Well,
I tried. My call button is
That's
oh, wait a minute. Maybe it's hold on. Let's see here.
Remember, I asked you about that, and you said it didn't matter, and it didn't.
Yeah. I'm not sure. Well, for this one, it does. It's only gives me a red call button. So Amanda, you gotta get off your Do Not Disturb setting for me to call you. Just so you know.
Yeah, she actually writes, do you actually really want me on?
Well, if we didn't, we wouldn't have asked you.
Yeah.
So get your butt over there and get her done.
Yeah, Amanda, because I can't get any chat questions without you on here right now.
All right, let's find out if we can get her in on this.
All right, let me jump in to see these.
Hello.
Amanda, are you with us?
I am here.
She's there.
Oh,
very good.
Oh, that's really cool. Neat.
There we go. Oh, we got 3 of us.
Awesome. And my stream.
I hear an echo though.
You do?
Okay, wait, hold on.
It's got to be you.
Okay. No, okay, I think it's gone now, sorry.
Okay.
Okay, am I too loud? Am I?
No, you're
good.
fine. You're absolutely fine.
Hi, everybody.
All right, let me.
Wow. All 4 Galilean moons.
I know, isn't that pretty? All right. Yeah, I'm gonna just I just gotta check and see. I might have here we go. I gotta focus now because it's just a little bit off. I imagine I'll have some complaints from several people about my inability to, show things zoomed in as much as they should be or whatever. You still there, Amanda?
I am here.
Okay, good.
I'm hearing an echo every time I speak, though. But then it goes away. So I
Yeah,
don't know what's going on.
mine's like that too. Every once in a while, I catch an echo of myself or something. But
Was anybody else hearing you? Echoey?
I don't know. I just asked.
Okay.
Dapple says sounds okay.
Okay, cool.
I think Bill said something yesterday. Could the microphone on your camera be on?
No.
Causing the feedback? No.
Yeah, he's right. It could be, but it's not.
Okay.
Check that first. Yeah, we checked that first. Here at the EIB network.
EIB network.
And boom.
I'm trying to open up Stellarium since I don't have to run a feed tonight because I want to see how it's lining up with everything else.
Well, you know what? Actually, I also discovered that Stellarium causes a data dropout. Oh, you know what? I'm wondering why all of a sudden my camera went black. Battery change.
Uh-oh.
Yeah, no problem.
You didn't go with the battery pack either?
I didn't yet because I got such a tremendously good deal on these batteries.
Bill was kind of scared with his
Well, Bill actually
camera, but I think he got one that actually wasn't wasn't meant for, or it wasn't the same brand, like the same company that made it or something like that.
Yeah, I see. Even B&H Photo makes one that's not really the right one for your camera. And that's kind of crazy, but even they don't get it right sometimes.
Now, Mark, is what you're showing, is that real?
Yeah, it's real. We do have a Jupiter. No, I'm sorry. What do you mean?
No, I mean, sorry, it's a whole bunch of noise just entered in. Is that it's not a mirrored image or anything?
No, it's actually the image is not. See, I keep forgetting. I had another setting I had to pop out here. Okay, here we go. This is, if you look here, okay, I'm looking to see where the, if we see a red spot. I believe, okay, that, is it south is up right now? I think that's what I'm seeing here.
I'm seeing a spot.
Me too. I don't see any. Oh, got closer. Oh, closer.
Yeah, it's getting closer, yeah.
Don't see any red dot, though.
Yeah, I do not believe the storm is visible right now, but if anybody's wondering about the moons, all the way to the left side of Jupiter, you got Ganymede, and then right next to Jupiter on the right-hand side, you got Io, and then the next one out is Europa, and then the furthest one out to the right is Callisto.
And that could, it's not always the case that the furthest one out is Callisto, because, it could just be that when Callisto goes on the other side of its orbit a little bit, that it could even look like it's closer than Io.
Yep.
Jupiter.
As I said, just the perspective of how we're seeing it now.
Yeah.
So they can classify them.
Yeah, if you look, this is something that's a little different from with Paul's stream, which I've noticed is he has a system whereby to show the moons he has to actually completely overexpose Jupiter. All right, and I'm doing it without overexposing Jupiter. I'm just trying to. I've got Jupiter, and you can actually see the moon. Now, it's a little bit less contrasty, and maybe that's what it is, but, I have an f6.3 telescope here, and I'm just going to defocus for a second. I believe I may actually have some dew on the telescope, because it's been open for a number of hours. So it's possible. So, anyway, what I was saying was, we actually, when we look at Paul's version of the planets and so forth, it does look different from mine. And I think that, it has to do with the speed of the optical system. It also has to do a great deal with the camera. And the camera, being the A7S II, it has a much larger range of exposures that you can use. And it is kind of interesting to watch this thing, because you can actually see how it. You can actually see how this. I'm sorry, I'm kind of preoccupied here. The dome started moving by itself. It's like ghosties. You can actually see how the moons themselves are aligned with the cloud bands on Jupiter, so to speak. Okay, they're in the same plane, and that's the same plane that Jupiter's ring is in. And I've seen some things online recently. There's been folks that have actually put up images saying, "Oh, look, it's Jupiter's ring," and they show these photos, and it shows the ring kind of canted at a wrong angle to the moons and to the bands, where the bands would be. So that was telling me that no, actually, that's not Jupiter's ring. And that person quickly took down that post.
I mean, is it even possible to photograph any rings from Jupiter from Earth?
Actually, it is. And the thing is, though, the conditions have to be really good, and you have to be able to do a proper exposure. You have to be able to do it in such a way that you don't require the rings to be backlit. And there is a way to do it. It can be done. It has been done. But you really need a very, very, very large telescope. And but if you do it, it's going to be in the same plane that we see, the same left to right, well, kind of upper right to lower left plane the moons are in and that the bands are in.
So even still, they would still be hard to see even with a perfect exposure of it.
Yeah, absolutely. And the thing that's interesting is when you look at Jupiter and you look at other planets, all right, Jupiter's not the only one that has a ring. Obviously, Saturn has a ring. Okay, we also have rings around other planets. Our Earth doesn't have a ring, but it does have one large moon. And that one large moon is probably so cratered because in the impact event that created it, that struck the moon, struck the Earth, during that impact event, all the stuff that was shot off did become a temporary ring around our planet. And then, of course, that was chewed up, eaten, and absorbed by the primitive baby moon. And so that was responsible for a lot of the craters that appeared on the moon over time. But it's pretty interesting to understand that we're seeing these things in these planar conditions, right? You have to wonder, well, how come? Why weren't the moons all over the place? How come they're all in the plane? And that has to do with when during formation. They weren't always like this. So you do have to wonder why we don't have moons going north to south around Jupiter, and why we don't have moons going at a 45-degree angle and on a weird orbit like like we see in the classic Adam cartoons. And the reason, of course, is because when everything is forming, they start there's a cohesion of stuff that coalescence of objects all come together from all directions. Then they start to spin around each other. There's an accretion disk that's formed. That is a disk of material that forms predominantly on the plane of rotation. And that plane of rotation and the particles in it have their own gravity. And they pull in objects, they pull in other stuff, and they end up making the disk object stronger and thicker, and then objects form within it, which become protoplanets or proto-moons. And at the center we have a protoplanet, and then these little proto-moons are little collections of areas around in that disk of forming material around a planet like this that's going to make a set of moons. The little areas around it that actually form knots. And those knots have gravity, which then pull in more stuff, and then those pull in more stuff and more stuff. And they eventually sweep that area that they're rotating in and orbiting clear of material. And that's how come we don't see any remaining dust and debris, say, in this Jovian system, in Jupiter system. We do see the results of a moon that's too close to a planet when we look at Saturn. I mean, Saturn may have had a moon that was drawn too close. And when that happens, the differential gravitational forces that are on it will actually rip it to pieces. Okay, and that distance is called the Roche limit, R-O-C-H-E. And that Roche limit is a absolute minimum that you could have an actual formed moon. And if you're inside that limit, then the gravitational forces and tidal forces from the planet will shred the moon and take it to pieces. And that's, probably what happened to Saturn. We'll never know. It could have formed that way too. It could have been that was leftover debris, but we'll never know. So it's fascinating stuff.
Awesome. Well, I'll tell you what, Mark, I am going to head out. I'll leave it to you and Amanda to finish up tonight.
Okay.
And thanks for having me on.
You know what? I really enjoyed it. I'm glad you could come on with us, Keith, and I appreciate your support for the SkyTour LiveStream. And this is day 2, fabulous evening, and there's a couple more things planned, and as the night wears on, maybe we'll check them out.
Yeah, not just tonight, but keep an eye out, people. This year's going to be big. You're going to get a lot of stuff done this year.
Oh, you betcha.
So. All right, guys. I will talk to you all later. Amanda, Mark, have a good night.
Thank you. Thanks, man.
Thank you.
Yep.
Now, when you hang up, are you going to disconnect Amanda?
I don't think so. So you might have to call her back, but I think I'm good.
Okay.
All right.
See
you later, guys.
See ya.
Bye.
And you're still there, right?
Still here.
Awesome. Cool. So yeah. Anyway, I can't see in chat. I don't know if anyone's asking questions or the 3 people watching. I don't even know how many are watching. Are talking amongst themselves.
Right now, I see 24 watching and 24 blue little thumbs. So very, very happy.
That's pretty good.
This is wonderful. Yeah. Thank you, everybody out there in chat, for your support. If you have any questions, send them in.
Yeah. Cool.
Yeah, no, I mean, there were a few issues at the beginning, but people are just listening, loving the views, just in awe of it all. So we'll see if any questions come in.
Yeah, that's a good idea. And you know what I'm going to do is I'm going to come off of Jupiter for a minute, and I'm going to head to another object that I'd like to show people because it really is interesting. And I showed it yesterday, but you know what? I'm going to do it again because you can't see this one too many times. And I didn't want to go back to it. I don't have to. We shouldn't have to go back, but I'm going to do it because it's just so cool. Moving.
And by the way, I don't know if other people appreciate it as much as I do, but I like when you say, okay, I'm about to move over somewhere, because the first few times that telescope started moving, I almost jumped out of the seat, so.
Oh. Sorry. But
well, at first I thought it was like some little sound effect you were adding or something, and then I realized, oh no, it's actually the machine moving, okay, and
yeah. Well, unfortunately, the way this has to work is that, I have to be able to see what's going on, and I have to make sure that I'm telling people what's going on, because if I don't tell people what's going on, then they will be surprised, and it will be a problem, and I don't want it to be a problem. And sadly, there have been accidents in observatories when people don't announce what's going on. And I caused one of those accidents in a very, very big observatory. And I'll tell you what happened, because you know what? I owned up to it. It happened. It was my fault. I was working with a 20-inch refractor. That means a refractor telescope. Those are all lenses, right? Not mirrors. So this 20-inch refractor was actually in a big observatory, and this big observatory was a research observatory, and I was actually using this telescope to do some research. And it was a multi-million-dollar instrument, and it weighed several tons. And I took my eye off the ball for 1 second too long, and what ended up happening was the telescope ended up, it has these large weights on it. The telescope ended up slamming into a pier in the observatory, and it was a steel bar, a cylindrical piece of steel that was meant to be a railing, actually, for preventing anyone from, falling down into what's called the scope well, the hole that is down there under the telescope. And the bar just bent like it was not even there. and it was so unbelievably frightening. And that was like, wow, I could have caused millions of dollars of damage, and luckily it didn't, and luckily I wasn't fired from my job doing it. But I'll tell you, it was a harrowing experience, and the worst part is if you do that when you're riding the telescope, when you're actually in the telescope and moving around, and that actually happened to me with one other little episode, and I was sitting on a giant ladder that was up against the telescope eyepiece, and I was making an adjustment, and I put the control box down by my right leg, and I picked up my leg and I kind of sat my butt on it to kind of hold it from falling. And as I did that, it started to move because I pressed the button without realizing it. And it moved me, the whole ladder and everything, and I could hear steel bending and breaking and twisting, and it was trapping me in this cage of steel. This multi-ton instrument was sitting over my head, and this was a different telescope entirely, and I was like stuck inside this ruined mesh of cage, telescope cage, and it's like, wow, you know, I'm gonna die in a freaking telescope cage.
Oh my gosh.
Luckily I didn't, and I was fine. But let me tell you, it was just like, you know, you can't take your eye off the ball with this stuff. You know, you really have to know what's going on. This, by the way, is something we saw last night. It's called a globular cluster, and this is called Messier 13. Charles Messier in the 1700s started to come up with a list, as I said yesterday, of objects that he didn't want to have confused as comets. And he unwittingly created this catalog, which is you know, wonderful for all of us that love to hunt for things. And I'll take a picture right now. It's going to be a 5-second picture. Let's see how it turns out. So the screen goes black for about 5 seconds, and then you'll see it come back, and you'll see the image.
I think that's really cool. I really, really like seeing that yesterday and today.
Well, this shows you how the camera sees it initially, and then how it sees it when you actually take an exposure. All right, and then when you see the photo come up, you're going to see how beautiful it looks, and it looks so much better than last night. I really, really like this. So you'll see it, and you should see it just about now, I would guess. Is it there yet?
I'm not seeing it yet.
It should be black, and then you'll see it pop up, and then it'll flash as I, you know, as it.
I'm waiting for the flash, but
You should see it. It'll be there. You can.
Oh
do it.
wait, it disappeared. Hold on.
Yeah,
I think
and it comes back.
we might be getting something. Oh yes. Wow. And of course, my voice is not going to be matching. What you're hearing Mark say is going to sync up, but since I'm watching it on YouTube, it's going to seem like I'm seeing it 30 seconds after everybody else.
Well,
but
that's
I'm not.
because you really are, aren't you?
I'm watching it with everybody in YouTube.
Right, and I'm treating you as if you're one of the people on YouTube. I'm not expecting you to see it now because you can't. Mm-hmm. I'm seeing it immediately. You're seeing it 30 seconds or whatever later, and I understand that, and I'm sorry. You know,
as long as chat understands, they're going to be like, "Oh, I think she's lagging."
Oh, I see. Isn't that pretty though?
That's gorgeous.
Yeah, and so that's how the camera sees things, and I'm telling you, it's just so beautiful. I absolutely love this.
So, okay, explain the whole Messier thing. Okay, so he was only looking for comets, and he'd find these things, and he'd say, it's not a comet, so what, I don't care, and let someone else kind of figure out what it is, and that's what they do?
Yeah, sort of. Isn't that crazy? And so, you know, basically, you know, what he did was, he ended up creating this catalog, again, unwittingly, of objects that could be mistaken for comets, and by doing so, he created the most famous catalog of objects for people to try and you know, hunt down that they ever could, and it's just amazing how this came to be. And you know, when he actually made this, that catalog, he ended up you know, being, you know, just angry that he couldn't, you know, find comets initially, and so he just put these things aside. And it turns out that they've taught us more about the universe than anything else that we've done. So I think it's pretty cool, you know. And so that's Messier 13. That's the the globular cluster in Hercules. It has about 100,000 stars. It's maybe even more actually, and it's really massive. And it's actually an object that's out in the galactic halo, meaning it's not even in our galaxy. It's outside our galaxy, and it orbits our galaxy. And I remember yesterday I said that the stars that made this were population 1. That was wrong. They're actually population 2 stars, and I was in error. And the reason I was in error was because I put the cart before the horse. Population 2 stars are the older stars in this galaxy, okay, in our universe. They're metal poor. They don't have metals, meaning anything other than hydrogen and helium, basically. And those stars were one of the among the first ever created. So when you see objects like this in the sky, you're seeing back, of course, way back to the time when they could actually be seen. But you're also seeing you're seeing back to a time when these stars that you're seeing there were actually, when they were first made, there were no metals in them, there were no other chemicals in them. So they're all clustered together. So it looks like the universe was a very strange and different place back then for this to be this way. And so I just think that's just incredible. Now, this cluster you're looking at right here is 23,000 light years away. All right, it's outside of our kind of outside of our galaxy, and it's at a high galactic latitude. It's called. So it's really one of those objects, and it circles the whole galaxy itself. All these stars are circling each other. I mentioned that yesterday. And they're also circling the galaxy together as a unit. Talk about solving what we call the n-body problem, where you have all the solutions to motion for more than 3 objects. It becomes this massive undertaking. Just imagine solving it for this giant cluster of stars. It's crazy. And we don't even know if there's something at the center of this cluster that's holding it, like a black hole. We know that galaxies have massive black holes at their center. Which actually acts as a cohesive central force. But then, obviously, objects like this, we don't know. We think maybe their mutual gravity is what's doing it. So it's pretty cool. I think that when we look at objects like this, it gives us a glimpse to the ancient universe. Because we're seeing this, obviously, as it was 23,000 years ago. And that's amazing, just incredible. So, and this is how it looks to the camera, when you're using a special camera to kind of just barely see it, as you'll see it come up. So it's kind of cool. And I wanted to take you to another object tonight, which we also saw. But I want to show it to you because it's a better night, and I think it's going to actually look better. So we're going to go there now.
Okay.
Moving.
See, that's the thing. I mean, I love being invited on, but Bill or Mark or Paul would be much better because I don't want to dumb the show down. So, while you're moving your telescope around, we have a few questions. So,
sure.
Paul wanted to know: are public scopes allowed to publish images of the moon without approval?
Absolutely.
Good question.
There's no reason why they can't.
Yeah. Okay.
Yeah.
Now, okay, now I think, I don't know if these were answered. Okay, Fantasy said, isn't Enceladus responsible for Saturn's rings, at least the F ring?
Responsible? I don't think responsible is the word. I think, Enceladus is definitely spewing material, okay, but it's actually then going back through that material as it traverses around Saturn. But there's other small moons that are responsible for altering the rings of Saturn. Among them are moons that they call shepherd moons, and that's more what's responsible for Saturn's rings. Now there's the news and the people in the news, they don't have timely information for us, so when you hear them talk, you don't really get a good feel for what things are because they themselves don't know what they're talking about. Did I say that out loud? I think I did. So
That's not live. We'll just edit it out.
right, exactly. But in Enceladus' case, it's only 300 miles across, but it does have a great impact on Saturn because of the fact that it has a tremendously active system at its south pole, which is spewing this water vapor into space, and it's freezing. And it turns out that water vapor also has hydrogen in it and carbon dioxide, and that tells us something very important, because that's telling us that Enceladus may very well have geothermal hotspots, just like Saturn, and just like on the Earth we have in our deep oceans. This could mean that Enceladus could be the first place that we actually find life, because we might actually find microbial life on another place in our solar system, and it might be at Enceladus. That 300-mile moon could be the place, and if there's anything there, we certainly would go to Europa, because Europa is another. And there is a mission called the Europa mission that is on the docket to be done, and hopefully we can do it. If we can't, well, that's the way it is. But it's a budget thing. So okay, now can you all see that little thing in the center of the screen? See that little thing? Looks like a donut.
I'm not seeing it yet. I'm seeing, I don't know, it kind of looks like maybe a constellation.
Well,
Probably not, but
you should see it.
I see like 5 stars on the left, a really bright one on the top.
Yeah, and you see a little donut kind of in the center there.
Oh my god, my eyesight's so bad I don't see a donut.
Well,
Maybe chat sees a donut.
I've zoomed in a little bit, and I've actually put it pretty much in the center of the stream, and now you'll see it a little better. And if I go a little farther in, it's a little more distended. Let me go back out and pop it back in. So there it is. Now, do you see it now? Is the question.
Okay.
You see that little donut thing? It's right there in the center.
It almost looks like a smudge to me, but I know what you're looking at.
Okay, good. There's a reason why I'm doing that. Okay, it's not to make your life difficult. I'm gonna now take a photo of it, because this is what we do as astronomers. We take photos of things that we don't understand. So this is fairly dim. So at 10,000 ASA, I'm gonna take a 5-second exposure. Okay, and here we go. Yeah, we're taking the picture. Now 5 seconds later, it's gonna come back. I'll see it here, and then you'll see it there.
That was another question. Mr. Spirit asked if the time exposure was 3 seconds, but it's 5?
This one's 5, yeah, and the
5 seconds.
The one for the Messier 13 cluster was also 5.
Okay, because he said the same as yesterday. Were you using a 5 yesterday as well? 5 seconds?
I might have been, but you know what? I can show them. I can actually show you and go to take ridiculously long exposures. You might enjoy it. So now you'll see this a little bit zoomed, and it'll come in. So now you can see it. I don't know if you see it. You should see the color.
I saw it for a second. Okay, there we go. Yeah, it's back.
Yeah.
It's blue.
It's blue on the inside. It appears. It's actually a greenish blue, and then on the outside, you see the orangey red color, right?
Oh, it disappeared.
And then you're gonna see it bigger. I'm gonna kind of just bring it back and zoom in a little bit. Can you see that?
I see it.
Yeah. Now, when you look at this, for those of you in chat watching, you can actually see a very faint little dot in the center. And this is what we talked about yesterday. That's actually a white dwarf. It's a star at the end of its life. And this ring, this is actually called the Ring Nebula. This ring, which is right here in your summer sky, it's going to be overhead in about an hour and a half. This ring is actually what's called a planetary nebula. Now, it's also Messier 57, and the reason it's called Messier 57 is because Charles Messier said, hey, here's another stupid thing that's not a comet. I'll call it 57, literally. And that's what you got here. So Messier 57 is a planetary nebula, so named because it could be mistaken for a faint planet, because it kind of looks round. That's why I wanted you to see and look for that round smudge, and that was good, because you've proven the point that Charles Messier was trying to make also, and that's exactly what I wanted. Now, the ring appearance is funny, because if you're anywhere else in the universe, looking back at that star, it would also look like a ring. And if you're on the other side of it, looking toward Earth, it would look like a ring. If you're above it, looking down, it might look like a ring. From any direction, it might actually look like a ring. Now, there's a reason for that. The reason is because if you have an expanding sphere of gas coming away from a star, which is what happened here, then at the edges, where you're looking through the most material, it'll look thicker. But the center is the material that's coming directly towards you, and at the other side, the material going directly away from you. And that's thinnest there. So you'd actually see through it to a certain extent and to a certain distance on either side. The overall effect is that you would see a ring. And that's why this is called the Ring Nebula. Now, some recent research actually shows that we may actually be looking down a tunnel that happens to be coming right toward us, or slightly toward us. And that tunnel would be oriented in such a way that it just happens that we're looking straight down inside the opening of the tunnel. And that's because these planetary nebulae show a curious feature called bipolarity, just like some people, okay? These nebula are bipolar, and they actually show a really interesting phenomenon where they will look like they're actually spewing material, say north and south, but not east and west. And that's kind of what we're looking at here. So hopefully you can all see that, and I think it's actually a really pretty object.
It's gorgeous. It's
a little gem.
I don't know, when you were describing that, it's almost like I wanted to think of it backwards, and I really, really had to follow what you were saying, but like, it's almost like once you flip that way of looking at it, it's quite overwhelming. Just like, because when you were saying, like, I don't know, and again, maybe it's just me, because I think a lot of people listening have had more experience and kind of had this as a hobby and an interest anyway, but like, the stuff at the edges being thicker and the stuff at the middle being, like, thinner.
Yeah.
Like, that almost seems backwards. But yet, the way you explained it, actually, it makes sense, and
well, another way
you took the picture down. I thought your battery died. Okay.
No, I just did this. Another way to look at this, if you turn your hand sideways and you have your fingers spread, you can't see in between your fingers, right? But then if you face your palm towards you, you can see through your fingers because you don't have any skin or anything blocking it. Okay, so the front and back of the nebula is your palm facing you or away from you, and the sides are trying to look through your hand, and you can't because you've got fingers through there, right? So that's how this works. If you kind of do a little circle with your hand and go and kind of follow the contour of that nebula and go right around, you can see at certain points you can see your fingers, and at certain points you can't. You can see through it, and at certain points you can't. And that area where you can't see through it is the edges. And then the front and the back you can see through. So it's narrower, less obstruction. And that's kind of what I'm getting at here. That's sort of how this works. Does that make more sense?
That makes tons of sense. And that's why this channel is going to be so huge, because you have such a nice way of explaining it that, I mean, I don't know.
Well,
I would assume that almost everyone here has at least one hand that they could actually do that experiment, and now I can understand what you're saying, you know, like...
That's true. I mean, I think that, you know, as long as they have at least one hand, they can do this. If they don't, then they have to get a friend to help them.
Oh, I'll get a tweeted by someone else on their behalf.
My hands are weak.
How cruel, how inconsiderate I was.
Yeah, well, you know, that's what happens.
Mm-hmm.
Yeah.
So is it the denseness then that's changing the color around the edge because it's thicker? It's a different color.
No, it's actually the actual interaction with the remains of the star in the center, because that's actually 2 to 3 light years across right there that we're looking at, and the star is still bright and has enough energy so that it can actually cause the gas to absorb some of the energy and then spontaneously reflect it, or drop it, an energy state out of the atom, and it will give off some light. So we actually see this gas. So we may catch oxygen in here, we might see some hydrogen. And that tells us what it's made of. And that's an example. This, like I said, a planetary nebula, but this is a star that has died. And that central star in the center is just that white dwarf. That's what's left. It's the hot core left over the star, and it's going to eventually cool and become a black dwarf. But that material is going to eventually spread out and become new star material or planetary materials somewhere along the line. We've had billions of supernovae, which were not this, but billions of supernovae where the heavier elements in our periodic table, except for the exotic synthetic ones, were made. And then in neutron stars, some of the materials were made that are in our periodic table. This star probably made up to about iron in our periodic table, and then that material ended up being returned to the interstellar medium when the star died. Now, this star was burning hydrogen into helium normally. That's what stars do. That's called fusion, nuclear fusion. And then, as the star ran out of hydrogen, it began to put out less radiation pressure from the hydrogen fusion reaction, less outward pressure. And a star lives by this, by equilibrium, by this, it balances its own gravity trying to collapse it, and the outward pressure of radiation pushing it out. So that's called hydrostatic equilibrium, and the stars all maintain that. Every star you see around there has hydrostatic equilibrium, okay? And except for the central star we're looking at, this object that made the Ring Nebula. And when the hydrogen fuel starts to wane, well then the star begins to shrink a little. And when it shrinks, because it shrinks, it's getting hotter, more heat is generated, and it begins to burn helium into more materials that we see in our periodic table. And it starts burning in what are called shells, like onion skin around a star. It starts burning helium in certain shells, the remains of the hydrogen in certain shells. Carbon gets burned in the shell, and nitrogen and oxygen, all the way down to iron. Iron can't be further combined with anything else. Iron is stable at that point. You can't do anything with iron. So it becomes the core of the star. And when the star is too massive, big giant star, it doesn't die gently like this star did, just by sloughing off its outer layers once it ran out of fuels and bloated and then shrunk again. The stars actually, the bigger ones actually explode in these massive supernovae. And later on in the summer, we're going to have the ability to see a supernova remnant right near this actually, but it's not quite high enough to actually see. It requires some careful guidance to get to, and we have to really take our time getting to it. And I'll probably pre-find it the first time, make it the first object we find, and then we'll image it a lot and take a lot of pictures of it, and you'll see it's got a very delicate filamentary structure to it. It's called the Veil Nebula in the constellation Cygnus, which is right next to this constellation, which is Lyra. I mentioned yesterday that Cygnus has a bright star called Deneb. Deneb is one of the 3 stars that form the summer triangle. And that triangle is formed by Vega, the brightest star in the constellation in which this Ring Nebula is located. Vega is the brightest star in Lyra. And then Deneb is the brightest star in Cygnus the Swan, which is next to it. And then Altair is the brightest star in Aquila, the Eagle, which is the 3rd constellation in the summer triangle. So we have Cygnus the Swan, Lyra the Harp, and Aquila the Eagle. These form the 3 dominant constellations that we see in the summer. And so we see a lot of, the Milky Way runs right through Cygnus. So when we get the Cygnus Milky Way really high, oh my gosh, you're gonna see, we're gonna be able to image some incredible nebulae and stuff without a moon in the sky, and it's just gonna be spectacular. So whereas it seems like maybe in these initial streams we're kind of sucking wind a little because we don't have too many glorious objects. We actually do, but we have a moon. So we either image the moon, or we image Jupiter, or image Saturn, or we can do star clusters and things like that, and brighter planetary nebulae like we're doing here. But I do want to show you one thing now, which I've got set in here, and it's called Beta Cygni. It's the second brightest star in the constellation of the Swan, the Cygnus the Swan, and moving. Yeah, well, you know, just making sure that you understand what's going on.
See, but I mean, I think, like, I was telling people today, like, you would not believe the images that you were showing us last night. Like, it was just unreal, and, oh, well, we'll just jump over to this star, and we'll just jump over here, and we'll zoom in here, and take a detailed picture. I mean, it's unreal. So to say, you know, oh, we could just look at this or that, there's nothing really that great. This is mind-blowing. This is incredible. And to actually be able to ask questions, like, I don't know. So many times, like, you can see this stuff, but it's like, what are you looking at? Okay, well, I'm just assuming I'm looking at stars, but that's about it. But, you know, that you're actually taking questions and explaining it so well is just, I don't know, it's unreal. And
well, I'm glad you like it.
Forget us when.
Oh yeah, right. So I showed you this real quick, and I'm only here briefly because there's one more thing I want to try and find in just a little bit after this. But this is the N star. It's the second brightest star in Cygnus the Swan. It's Beta Cygni, it's called. And I say beta because alpha is the brightest, and it's the whole Greek alphabet, and I did recite the Greek alphabet yesterday, so you could tell I know it. It's an astronomer's thing. And I got really good at doing it fast. I also memorized the periodic table of the elements to a song, but don't ask me to sing that.
Copyright issues.
Well, if I sing it, it's not, but you know, it just goes on, and it's really, really good. It's a good song.
Before I forget, and I don't want to interrupt you, what was that Eurifying Guy Kiss Me? What was that supposed to be a memory trick for?
That was a memory trick I learned when I was getting my astronomy degree that was about how you can memorize the different types of stars. For instance, O stars are the hottest, and it bears repeating, okay, because it's actually interesting. O stars are the hottest stars, and they actually have, oops, I'm going to slow down the speed here. They actually have a very short lifespan, sometimes only a couple 100,000 years, or even at most a couple 100 million. And then they usually and will always typically explode in a supernova. And that's something that, you know, you don't want to be near. You wouldn't want to be near that, let me tell you. Okay, I'm getting these strange artifacts here from the low altitude. And then B stars are next, and they're like the Pleiades stars, the Seven Sisters. Those are B stars, and they have blue nebulae around them, and that's reflection nebulae. And then next comes the A stars, like Vega, the bright star that's right near that ring nebula we saw, and that's bright white. And then F stars are next, followed by G stars, of which our sun is one. And then we have K stars, which come next, which are a little bit orange. Our sun's a little yellow. And then we have M stars, which are more reddish, and they look like, they look at noon like the sunset sun. And they're not as bright, but they are very powerful for us in the exoplanet world, because most of the planets are around M stars. So we find them, and you know, I talked about on a radio show yesterday, I talked about the TRAPPIST-1 system, and TRAPPIST-1 was that system we found, which had excuse me, 7 planets, all within the distance of Mercury to our sun, to their star. So they were closer to their star than Mercury is to ours. All 7. And 3 of them were in that star's habitable zone. So you say, wait, huh? Mercury is nowhere near this habitable zone. In fact, it's hotter. It's hot enough to boil lead on Mercury's surface. How can that be? Well, it can be because the star is only 8/100ths, 0.08, okay, as powerful an output as the sun. So it doesn't have the output that our sun has, and 3 of the planets around the TRAPPIST-1 star are actually in that habitable zone for that star. That's absolutely just astonishing. So that said, we're learning some really cool things, and TRAPPIST-1 is one of these red type stars, an M-class star. In fact, it's like an M9. When I say 9, I referred earlier to the fact that when you talk about stars, they actually have the ratings 0 through 9 within the letter classification for their spectral class. So an A0 star is like Vega. Okay, a G2 is like our sun. An M9 is like TRAPPIST-1. So it's really the lowest temperature of the low temperature stars. It's also called an ultra cool dwarf. Hey man, I'm cool. I mean, it's sort of it's a cool thing, but it's also an ultra cool dwarf. So we see so many fascinating things out there, and this particular double star in Cygnus is another one of them. This is this is that tail star I was telling you about, Beta Cygni, second brightest star in Cygnus. It's called Albireo. And Albireo has a beautiful golden colored star and an indigo colored star, kind of like the almost purple. And these are binary stars. Now, Albireo's main component, the bright one, is obviously a very different star than the blue one. And those types of stars are a perfect example of how, when we look at things, how we actually define what stars are, okay, and what types they are. So I will give you some of the lowdown here on Albireo. It's really kind of a gem, to be honest, and it sits within what's called the Cygnus star cloud, which is, part of the summer Milky Way that we'll see eventually. And one of the things I'm going to do, by the way, is when we do more of this, I'm actually going to also stream with this camera on a tripod for part of the stream, so you can see the Milky Way wide angle. And then we'll go into the observatory and then zoom in on some things. And so it'll kind of be, we're going to do like both. It'll be really cool. Now,
that is going to be cool.
It will be cool, So this star that we're seeing here at Albireo, and this thing is about 380 light years away. So it's not like nearby, okay? And remember I mentioned that the different stars, O, B, A, F, G, K, M, right? Mm-hmm. Well, that orange one you're looking at, that's a K3 star. So it's a K type, and within that it's K not 0, 1, or 2, but 3. So it's that's K3 in its level, and it's a normal star burning hydrogen into helium. Okay. Now the other one, the one that's sort of that bluish, well, that's a B9. So it's it doesn't have to be that the stars are the same types. It just has to be which one got more fuel, which one was able to form first, perhaps, that kind of thing. And there's a lot to it. So these two stars formed probably in some proximity near each other, or they were separate and then caught each other gravitationally. That's also a possibility. And there was gravitational capture possibly involved. Now, it's really kind of cool when we talk about Albireo, because it's always been like a test subject for me, because you look at it and you can clearly see those colors, right? You can see those colors. They're very, very obviously orange and very obviously blue. And if you can't see them, then what we have to do is one other little thing, and that is, let me just do this here. Let me move them. Get out of the way here and move them so we can. There we go. So again, now what my trick is for testing the colors. Some of you remember, I take the stars out of focus, right? Well, that's actually getting out of the field. Actually, that's pretty good. And right now, by taking the stars a little bit out of the field, like that, now you can see the colors very well, can't you? And that's because the human eye is better at finding or seeing colors when they're more distended, right? And that's what we're doing. We're trying to keep the colors distended. So, and that flickering, by the way, let's look at that flickering. That flickering,
It's gorgeous.
Yeah,
It's mesmerizing.
It is, but that flickering is actually the atmosphere getting in the way. As mesmerizing as it is, it's the atmosphere causing us to have a what we call a lousy night of seeing. So it's not really the best. And but again, that's that has to do with a lot of factors. Among them being that we have a problem getting a good sharp focus on nights that are not totally still. I mean, they're beautifully clear today, but the air mass, the air around this has been kind of difficult, So this is interesting, and I'm going to try and see if we can find one more little object here. Again, with the moon out, it's kind of hard moving.
Yeah, I feel bad. Chat, I'm sorry, guys. I've really been ignoring chat because...
What? How dare you?
Someone's gonna lose out, and I'm sorry, it can't be you. I mean, I really have to focus, but I mean, little things like that. Now that I know that little saying, just something like that. I might not remember what an O is or what an A is, but at least I have some kind of order. At least it's some kind of basics, So like, I don't know.
Well,
I think that it appeals to everybody because like. I mean, I'm just stupefied with how much information you're pouring out, and a lot of these people, they're answering before you can actually hear it on the stream, but they are giving you wows and asking the questions too. So it really is. I think it's going to be great for all levels, and even if you don't know what you're looking at, the images are so gorgeous it doesn't matter what you're looking at, but.
Well,
knowing helps. Knowing helps.
Yeah, knowing helps. That's correct, and I like that. I like being able to share what something is, and I really want the bright sky to. I wish the bright sky would just go away. I want to show you some things. So I'm gonna do this here. I have to. See, I also have to wear glasses, and when I have to wear glasses, it's like I gotta put them on to look at the screen, but I take them off to look through the telescope. So it's like
I should be wearing my glasses too, actually.
Oh really?
Yeah. I mean, you would not believe how close I am to the screen, and I'm still barely seeing some of these stars. Like I saw the little smudge on the last one we were looking at.
So really, then it was kind of like. It wasn't everybody's problem. It was only you having trouble seeing what was going on.
Yeah. Oh yeah, everyone else saw it.
Oh, okay. Well, that's better to know.
and I'm not on dark mode on YouTube either, so all the white background.
Dark mode is kind of important.
Yeah, but every time I go to night mode, it asks me if I want to start streaming.
Well, that's just an error in what you got set up. You don't always have to be in dark. I was in dark mode just watching YouTube. It doesn't matter, right?
No.
Is that true?
I don't think so. I don't think it matters if you're in dark mode.
Okay.
Watching. I think it's just easier on the eyes, but...
Well, no doubt.
When I go back and rewatch these, I'll have it on full screen because there's not going to be an active chat, right? I was just...
Yeah.
And when Keith was on, I could have grabbed questions and stuff, but we were all just listening. And
that's okay.
Now, if I follow chat, I'm going to be missing way too much. And this is so. This is unreal. Thank you so much. We are all so appreciative. I mean,
well, it's not a big deal, It's like, I just want to have some fun. What can I tell you?
Well, that's what Paul and Keith say too. They're like, you know what? We'd be doing this anyway. So why not hang out with some people and share it? But that's an awful lot of work, and doing it just out of the goodness of your heart is really, really cool. So
Yeah.
let's go. What did you have to show us?
I took a photo of the random sky here because I just wanted to show you something that is just interesting. You know, we see stars and we think of them as all just sort of like one basic color, you know. But I want to show you how that's not true. You'll see this here in a minute. This is not Albireo, the thing we saw before. Okay, when you look at this star and its counterpart, you will be amazed at the colors. All right, this star is these two little stars are another B star, but also another K star, just like Albireo. But look at the colors. They're actually very, very brightly different. You can actually see the colors immensely clearly. You can see just how easy it is to see these color changes. I imagine you see them now, right?
Yeah, it was still moving around. I think we're stopped now, though. It looks like a really, to me, it looks like a really, really bright white one, maybe the lightest tinge of blue, and then like orange.
I'm zooming in.
On top, like an amber on top.
Yeah.
If it's...
Is it zoomed in yet?
I think so.
Yeah? So it's pretty much filling the screen, right? Right?
Well, I can see a lot of other stars around it.
Yeah, but it's right in the center and you can see them very clearly. Yeah.
What colors am I supposed to be seeing?
Well, it's like a bluish, a bright whitish blue, and then you've got that beautiful, as you said, amber, more of an orange. But isn't that gorgeous? I mean,
it is gorgeous.
I mean, how about that? Just sitting right out there.
Is that a double star? Or
actually, those two stars are actually just in alignment with each other. They're not actually a double, but they're just the coolest. They're just the coolest happenstance, so to speak. And I really think it's cool. So I wanted to show you that, and that's another thing.
That is cool.
I just love little things like that, to be honest.
And then there's something kind of above and to the right a little bit, and it's a lot bigger and kind of yellow.
Yeah, that
like a faded yellow. What was that?
That was another star that was actually in the field.
Oh, do you know what star it was? I just assume you'll know all the names of all the stars.
No, not at all. It's a field star, and I don't know. I don't know all the names. Of course not. That's crazy. Why would you think I know all the names?
Because sometimes you do.
On a rare occasion, I do, but this isn't one of them.
I've heard you do live math, like astronomical, literally numbers, and
yeah, you know,
witchcraft.
Yeah, it's witchcraft. It's witchcraft. Ban the witch! Ban the witch! So yeah, but that's pretty cool. And
I had a question about double stars. Okay, if Gemini is Castor and Pollux,
yes,
but they're a constellation, they're not double stars. Why is it? I mean, I don't know. I don't understand how two stars can make up a constellation.
They don't. Two stars that are in the same region of the sky can be part of a constellation, but two stars that are very, very close together may be double stars. All right, and that's something that you have to just understand. You could see, like, if we had stars that were really close to us, and these stars were actually very, very close to each other and were gravitationally bound to each other, well then, yeah, I mean, we could have a giant double star system in the sky that was separated by, like, Castor and Pollux's separation. But we don't have that, and we don't have it because we don't have we don't have anything near us like that. That's just the way it is. I mean, it's just the happenstance of the universe. We don't have that. But we do have, like, for instance, the Big Dipper near us. And the Big Dipper is actually our birthplace in the heavens. We actually kind of come from that area, the Big Dipper. And that's kind of cool, I'm taking another photo here, 4 seconds. This is in the Cygnus Milky Way area, so you can just see the variety of the stars that you see here. And it's really just a beautiful area. And we're not even we're not even going in deep, because if we did, we would end up, overexposing and seeing moonlight and other stuff. But, oops. I'll show you the picture. Let me show the picture one more time. That's the image that you'll see coming up here in a few seconds. So I'll let that happen.
And Paul asked you earlier, I don't know if you're still here or not, what your favorite deep sky target was.
Oh, well, that's interesting, because there are, before I actually had a telescope of any reasonable size, my deep sky object was one, that could be easily seen by a small telescope, and that changes when you start to, get a bigger telescope, and you start to, have an easier way to set it up. When you get an observatory, then it becomes like, I have no idea what my favorite is. They're all favorites, because they're all fantastic. I'm having such a good time with all of them. But that's neither here nor there. I mean, the point is that when you look at something like, a big double star, all right, or something like a giant nebula, I mean, they're all gems. So I guess I don't really have a favorite. I would have to say, my old standby, which is, unfortunately is the way it is one of the ones that I really like the most is the Orion Nebula. And everybody loves the Orion Nebula because you can see it with your eye. It's massive. It's a star-forming region. It's got it all. It's got young stars. It's got old stars. Hey, it's the bomb, man. It's the bomb. So I really like that entire area. It's just beautiful. And so that said, I feel that for a favorite, an absolute favorite, I'd have to say, I'm gonna look and see if I can see it now. Oh boy, should I try? I don't know if it'll work. I mean, I could try. You're not gonna see anything right now. I'm gonna put the dome a little bit. Yeah, it's still in the murk. There's a nebula down in the constellation Sagittarius called the Lagoon Nebula, and it's absolutely, hands down, it's got to be the most amazing place ever, and that's kind of the place that I really like. I really like it a lot.
What kind of conditions would we need to be able to see that? Will we be able to see that on a future stream?
Absolutely. It's just got to be. It has to be kind of a moonless night.
Okay.
We have like a moonless night, and but you know what? I mean, we can always try and find it. We can always try and find these objects anytime, and see if we can see them. Like the Ring Nebula, you would never kind of go looking for on a moonlit night, but we did, and we found it, and it's beautiful, right? So that's all there is to it. We like it. It works well.
Yeah, we were on. You were on with Keith the other night, weren't you? When Paul tried to find Pluto.
Oh, I saw Pluto.
And he was like, oh, it's really small and not that focused. And everyone in chat's like, oh my god, it's so beautiful. Oh my god, this is the best. And he was disappointed because it wasn't like as clear as maybe something else he would have caught. And it was amazing.
We are our own worst critics when it comes to this. I can tell you that. I can tell you that. We are our own worst critics. So I'm going to take a little, this is going to be an 8-second photo. It'll be a little longer. And we'll now the thing is, when we take photos like this, you can actually see that the object you take pictures of, you notice 8 seconds zoomed in pretty heavily in the sky. You have to think, well, isn't the telescope going to move? Isn't the guiding, isn't the clock drive not going to work exactly right? The answer is yeah, it may not. The problem is, or the best part is actually, that even though that's the case, I'm using a camera that's really special. I'm using a camera that allows us to take an 8-second photo of something that would normally take 10 minutes to see well. And we're doing it in just a few seconds. That's the magic of these new cameras, this new camera that I have. So that's really cool. That's just a star field. It's just a star field in Cygnus. And every one of those stars may have planets. I mean, really, we're finding that all these stars that have planets is just so numerous. It's amazing and incredibly rich plenitude of planetary possibilities out there. And I really think that's amazing. I really do. I'm gonna try for one thing here, just to see if we can see it. And again, we'll try. I'm trying for the things that we can't really see because of the moon. But I think part of that is the reason I'm doing that is because of the moon. I want to push my limits. I want to push my limits. That's not good. All right, let's see. All right, go there.
So when you see like that last picture that you had up, like you can see so many stars, and some look bigger and brighter, obviously, and you can tell like that's because distance. How do you even measure that? Is it all just like estimated, or like, you know what I mean? Or is that just a ridiculous question?
No, it's not a ridiculous question at all. I mean, we find stars a variety of ways, and one of the ways, or we get their distances a variety of ways. There are certain stars actually in the universe which are like standard candles for us. They give us their distance because of, for instance, their variability, the way they vary in the way they operate. And we use these for instance, for distant galaxies. We actually can measure the distance of these galaxies simply by the way that we can calculate the rate of change of the star in that galaxy. And these are called Cepheid variables, and these variables allow us to see an incredible panoply of changes or distance rather, and it's amazing. It's great, and I think that the nice thing is that when we're doing this and we're actually trying to create a catalog or data of stars and so forth, we don't have one particular method that we rely on, and if that method doesn't work, we're sunk. We actually have a number of methods that we can rely on, and that's one of them. So Cepheid variables are good for long-range distances. We can detect the rate of flow of objects, for instance, away from a star. We can also, in the case of supernovas, a particular supernova that occurred, we can actually look at a supernova that occurred in just over 1000 AD, and based on the speed at which data flows out from a supernova, we were able to detect the size of it, measure the extent, and then that gives us an example or a understanding of how far away that supernova is. So that's incredible, and that's the kind of thing that it's really hard for people to understand, But it happens, and it's absolutely true, and that's something that we have to understand. And I'm feeling that moving forward, some of these techniques will be a little more obvious, a little more clear, and I'll be able to explain them a little in more detail. But we have to first get under our belts some things to look at first. And this star field is beautiful because it actually you see the variety of colors of the stars in this field without any problem. And it shows you that stars aren't just bright white. They're not just white. They're all colors of the rainbow. And oddly, the one color that seems to be missing is green. It's there, and there are green stars, but the color is a little bit overshadowed by other colors, and it's sort of an oddball color. So I don't understand why, and not many people understand why, but that's the truth.
There's not a green one in here at the kind of topish middle. There's a white one and a tiny little green dot. No.
No, that's not green. I mean, I don't know every star, obviously, and we could happen upon a green one. They are out there, but they're rare. But
why? What elements are in them?
Well, it's not so much elements, but it has to do with temperature, and the temperature of the stars determine their color. And they, look instead of the field. Oh shoot! Come on. Oh, I missed it. Crap. I missed something that you needed to see.
Just don't tell us it was a UFO.
No, it wasn't. It was a satellite. It was going right through the view, and I was trying to get off the view that was there to go back to the live view. We missed it just by a little bit. I'm sorry. But you know what? It's okay. There's going to be many more. There'll be many more of them going through the field, and that's what we see a lot of. So there will be plenty. And so let me go a little. Was that 25,000? Yeah. We're going to go to 25,600 ASA. And we're going to do a 1 second exposure, see what we got here. Okay, a little bit of noise. But that background fuzz that you're going to see in this photo, and that background haze, that comes with the increasing speed that you try to take your pictures with. You know, so it's not always perfect, but you know, it works. It does work. I'm gonna drop that down a little bit, and we're gonna go for slightly less noise. I get down back to go to 16,000. Okay. Now let's see if the thing I want is still down in the murk. Still down in the murk.
Get the pictures up.
Huh?
Pictures up on YouTube now.
Okay, good. That's about the fourth time I've knocked the mixer off the table here. You know, that loud noise you hear is the mixer falling. Let's go look at something that I know that you will like. So I know you know what it is. Okay, moving.
I couldn't even guess, actually. Something I would like. Are we going to look at the face on Mars?
Yes, we're going only to the face on Mars. Yes, you and Richard Hoagland can look at the face on Mars. Tell you what, I'll look at something a little different.
he's actually coming back to air tonight.
Is he?
Yeah.
Why? Oh, sorry, I mean...
That could have been my birthday wish. What are you doing?
Yeah, that's true.
Yeah.
I could have been mean, I guess, but I'm sorry. Okay, so now, okay, I visited this guy right here, and
you probably could see that whatever it is, mound of dirt, or whatever it is.
Oh,
Could you?
The pretend face on Mars?
Yeah.
Oh, sure, but you know.
Well, no, I'm not saying right now, but I mean, that's not a problem for you to find with your telescope, right?
Oh, absolutely. No one can see that with a telescope, except something's orbiting Mars. But, you know, what we could do is actually, we could actually end up just going to Mars through Google.
Yeah.
There we go. You'll see this in a second. You'll recognize this. Yeah, you will.
Will I?
Absolutely.
You give me too much credit.
No, if you don't know this, I don't know what to tell you.
Hold on.
No, I'm holding. Yeah, this is looking pretty tonight. At that end of the murk.
Oh. Okay, well if it's something that looks like Saturn and this is a horrible trick, I'm gonna be really, really upset.
It's Saturn.
Oh God.
It's Saturn.
Okay.
Yeah.
I actually typed in chat, help, what are we looking at before I actually saw it on screen. So, okay guys. Okay.
Right.
I didn't know it was Saturn, I didn't know. I didn't know what you were going to show me and I got scared.
That's alright.
It's gorgeous. I love it.
No,
I do love it. You were right.
I'm gonna take a little bit of exposure here of it, and it's gonna be overexposed for a reason. Alright. So it was fairly quick. Let me go even longer. Try 0.6 seconds at 16,000 ASA. Yeah, it's better. Okay. So when you see this, you'll actually see something very interesting, and that is, as you'll see in a sec. I'll let this come up. Saturn's going to be very overexposed. All right, and I'm not sure exactly. Some of the other objects in the view are field stars, but we also see Titan, which I believe is to the right of Saturn right now, and we see one of the other moons. I'm trying to think which one that is. I don't know. I'm trying to figure out which one I'm looking at. Sorry. I'll figure it out. I will know. So do you see it yet?
Yeah, you're just finishing the sound. Oh, and I hear the echo again.
Sorry, guys.
Yeah, I hear some noise, which is probably at your end, maybe.
I haven't done anything different.
Okay, it's just a little squishy noise there, like shh, you know. It's all right.
I thought that was almost like either wind or cars going by in your background, actually.
No, it's actually totally silent right now. Not
Yeah, it does. It sounds like wind whenever we're quiet, but anyway, sorry, go on.
No, that's right. That's what it is. It's kind of like whatever. So when we're looking at Saturn here, you know, one thing that you'll see is that you know, we have the planets in the center, okay, and the orbits are a little bit strange to us right now, and I'm believing that what we're looking at right to the left of Saturn there, I think that is actually Enceladus that we're looking at right there. And then we have a little bit, I can't see it really, to the right side, it's hard to see, but to the right, the main dot is Saturn, okay, and to the right actually is Tethys, and then just a little above that is Dione, and it matters a lot at the point where they are in their orbit, and you have to go way out to see Titan, and I'm going to try and find that for you here. I want you to see it. I want you to see it.
Is the orbit important because it squishes Saturn a little bit, or is that Jupiter?
Yeah, no, it's Enceladus gets squished by Saturn's orbit because Enceladus is sort of in an elliptical orbit. It's not really circular. So at some points in its orbit, it's a little closer to Saturn, and at some points it's a little farther away. And so that's what happens.
Do a lot of moons orbiting planets do that? Or is this kind of a rarity?
Yeah, no, it happens fairly often. It's not uncommon, and I believe that it's interesting when you look at something like this, because you know you're trying to see you're trying to figure out the gravitational interactions of one planet against another, and that's exactly the kind of thing that you would see. Is you would see that some planets actually do interact to the point where they actually do push and pull on the moons, and that is something that is very much part of the natural order, you know, and so that does have effects too. You will notice that the moons themselves may have a situation where you will find that the moon will actually be tugged and pulled so much so that something happens to it. At one point in the past, there may have been a moon, and that moon was destroyed by Saturn when Saturn was actually tugging at it so much that it actually pulled it to pieces. That's a strong possibility, you know. And we look here and see that, well, you know, I'm not sure that actually, you know, you can buy that, because you say, well, how can that be? You know, maybe the rings formed and were always there like that. That's possible. It is possible that those rings always were there like that. But it's unlikely. So, you know, there's a strong possibility that, you know, Saturn's rings were a moon at one point that was destroyed. Which is a little different from what you were talking about a few minutes ago, but it's kind of where I wanted to go. It's kind of where I was getting at. So I apologize for that, but, you know. Anyway.
I shouldn't have interrupted. I should have kept listening to the story.
No, that's fine, because I was actually trying to, give you some more information, and I kind of fumbled my way through that without really thinking too much about it at the moment. So I apologize. I'll get back to it. Alright, so. And always make sure that every time, make sure you watch for potential satellites moving through the field. And we are kind of zoomed right now, but it's possible that we'll see them. It is possible we shall see them. Okay, now we got that. Alright, here we go. Let me go
Looks
down.
like I'm got a little bit of buffering. I hope I'm the only one. Okay, it's good now.
Oh, good. That wouldn't be fair. Alright, let's go see what's
I'm still looking at Saturn. I don't know if you said you were going to move, but I don't know if you did.
Okay, I'm actually, alright, I can tell you now what those moons are. I figured them out. Let me go back and do this. See what I get to the point where it's like, alright, I gotta answer this question because it's making me crazy and I wanna try and get this straight. So, let's take another photo, of this whole system, and then we'll go into that photo directly and we will analyze it in depth. Okay, here we go. Now, here's the photo. Now, when we get close to this, alright, you see that the center one is Saturn. You see that clearly, right?
I see that.
That's that bright one in the middle. Now, Titan, which is obviously one that everybody likes to know about and discuss. Titan's actually right there. That's Titan, right there. It's that bright one that's roughly centered that'll come in a couple seconds. All right. Let me know.
Shifting. Yeah, it goes back.
Okay, got it.
Okay, so now Titan is basically center?
Yes.
Yeah. Okay.
And then, kind of almost lost in the glow of Saturn, but just to the right of that glow, you see that little dot that's there?
To the right, yeah.
To the right of Saturn, okay? And it's actually just
above the 3 o'clock, if it was a clock?
Yeah, just above the 3 o'clock. Mm-hmm. Okay, that is Enceladus. Okay, and then above Enceladus, which definitely is sort of lost in the glow. It's there, but it's Dione. You can't really tell. And then to the lower side of Enceladus, you can't see it, is Tethys. And then
we can't see it. Is it behind Saturn right now?
You can't. No, it's there, but you just can't see it because of the glow. Maybe you could take a picture.
Okay.
And then to the upper left there, you're actually looking right to the left side. That's Rhea, okay, and that one's the moon, the moons of Saturn that we're looking at right there. And there's Hyperion and there's Iapetus as well, but you can't really see those too well. But I think it's pretty neat. I think it's neat to actually be able to see these anyway, because that's something that is kind of rare, that you get to actually see the moons and actually see them. Let me just get this. It's rare to actually be able to see the moons this way.
It's unbelievable. It really is.
You know, so let's go do one more nice view.
Dee had a question though. Let me just go back to it. If the Earth had rings, would we be able to launch into space the way we do now? That's a good question.
I would think that almost nothing would change, actually, and the reason is because we would. Well, actually, okay, I totally lied to you, and I didn't mean to. I was thinking from a different perspective. If the Earth had rings, we would have an equatorial belt of rings, and we would no longer be able to do east-west motion with our satellites and put them in these orbits, because they may stand a chance of colliding with something on the rings. So that is a definite showstopper for us, you know, and that really would be very damaging to us. We wouldn't be able to manage orbit easily that way. Now, if we're going to the moon, or if we were going out to other planets, then those rings might not have any effect, and I'll tell you why. Usually when we do a traversal into inter-Earth moon space, or we're going out there, we don't go out over the equatorial regions of the planet. We actually go out to the north and south polar regions of the planet, where the rings wouldn't be, most likely. The reason we do that is because we're trying to avoid at all costs the exposure to the Van Allen radiation belts. Now, what are the Van Allen radiation belts? You hear a lot about them. You hear a lot of conspiracy. Well, the Van Allen belts are our magnetic field that traps charged particles coming from the sun. Our magnetic field is what protects us here on this planet. Those particles that are highly charged from the sun can kill us. And so they get trapped by the magnetic field, circulating through the magnetic field, and orbiting in the magnetic field and so forth. And I'm just touching the telescope to see if it's got dew on it, and I got a little bit, so we may be coming to the end of the stream tonight. And those Van Allen belts are actually very dangerous that way. And some of them are so low to the Earth, actually, that some of these trapped particles, in other words, are so close to the Earth that the International Space Station can actually travel through them a little bit at times. And when that happens, one of the problems that we have is that the astronauts have to move to a safe space within the ISS. That happens rarely, but it does happen. And they have to move for a few minutes, not long, because don't forget, the ISS is moving 17,500 miles an hour, basically. And at that speed, it doesn't take but a few minutes to get past a certain danger spot that's over one particular edge of a continent or something. Also, another fun fact is that the astronauts see 15 sunrises and sunsets a day. For us, a day for us is 15, one 24-hour period, but for them, they go around the Earth once in 90 minutes. So they see 15 of these a day, roughly 15 to a little more. It's pretty cool, and I absolutely love it. So it's really, really interesting what the astronauts deal with and how they actually deal with it. So these Van Allen radiation belts are, as I said, these trapped particles in our magnetic field. But without that, without that danger, we would actually have a great deal of trouble. We would have a tremendous amount of difficulty, and we don't because of that. I'm going to, we don't because we actually go out to the North Pole, that's what I meant to say. So I'm actually going to go to one more object here, because in pointing where I am, I'm actually pointing in an area where the wind is coming through the dome, and it's actually pretty frigid right now, which is kind of odd. So I want to get the telescope off of it. So I'm going to move now. Moving.
Jay wants to know, could we mine or vacuum Saturn's rings away from Saturn if we wanted to?
Could we do what?
We mine or vacuum Saturn's rings away from Saturn. Can we get the rings away?
That's a heck of a question.
It might have been a joke, but I mean...
Well, in a sense, if you say it's a joke, I guess, that's one thing. But the fact is, is it possible that we could actually, do something about getting rid of these rings? And the answer is probably not. Maybe over, say, a time frame of, say, 150 years, 200 years, 300 years, we can actually, maybe do something about Saturn's rings. But we'd have to have the technology to do that. And unfortunately, we don't have that technology, it's pretty difficult to have, the ability to grab something that's like, several tens of thousands of kilometers out from a planet and circles an entire planet that's, just smaller, a little bit smaller than Jupiter. I mean, we're talking a massive amount of material. Now, could we mine it over time? Sure, yeah, absolutely. And we probably would. It'd be very cool. Okay, this is Alpha Cygni. This is Deneb, the bright star. And I'm gonna just let me set up my parameters here. I'm gonna take a photo for you. I'm gonna take an 8-second photo, and I'm gonna do it at a fairly low ASA, say 8,000. All right, so this will be 8 seconds. So you'll see the screen go black, and then you'll have to count to 8, and then you'll see something. You'll see the star fields that are around Deneb. All right, and this is they're really pretty, without a doubt.
I was thinking that earlier. Like, I think these crazy questions because I figure, like, if you can think it, we might not have the technology now, but that's, how future advances is people come up with crazy things to.
That's right.
And I was thinking, like, what if, like, okay, just hypothetical numbers. What if, like, 1 million asteroids over 1 million years hit our moon? Do you think the gravity of Earth would suck them into a ring, like Saturn? Like, if enough things hit the moon to destroy it, what would happen to all the pieces left over?
Well, I'm pretty sure that what would happen is that we would get bombarded by all this stray stuff, because it wouldn't. The chances of it getting pulled into just the right orbit around the Earth are very slim. So it'd be troublesome.
So it only happened with Saturn because Saturn did it. It wasn't an outside element, right?
Probably during formation is when those rings formed, and Saturn destroyed that thing, but Saturn's a gas giant. So any of the debris that entered Saturn's atmosphere has long since, been destroyed and become part of the interstellar medium again, or blended into Saturn. So, not a good thing. So there's the
the picture's up. Yeah.
And you can see there's a number of stars. This was only like what was this? How many seconds was this? Did I say?
8. 8 at 8,000.
Yeah, 8 at 8,000, right? And you can see already that there's some weird kind of not haze, but Deneb has a strange reflection on it. That's just because of the brightness. But you can see a number of other strange things going on, and those strange things, that cloudiness you see elsewhere, those are actually tens of thousands of faint stars that you're looking at. They're just so small you can't actually see them. So we're looking at star clouds. This is what we're talking about. This is where astronomy becomes real. Where you start to realize that we're looking at some amazing structures out there. So if we go to if we consider that when we look at Deneb like this, and we see the constellation of Cygnus, the Swan, we're looking at something that's amazingly, I should say, it's an amazing fact that we're staring at so many stars, but that also means we're also staring at other worlds, possibly, and probably most definitely. So we're seeing, a huge number of additional stars and so forth that we're seeing out there. I think that we're actually we have more of a populated universe than we ever actually thought, and it's just my feeling, it's just my thought, and I'm very.
That has a nice ring to it. Populated universe.
Yes, and why would you say that?
I don't know. It sounds like something really inspirational. Like it should be the title of a book or something.
Yeah, you're funny.
Come on, Mark, make it happen. Write a book. We need a book.
Actually,
when's it out?
I'm putting, as I said, I'm putting all the illustrations in it now. But it is actually, it is coming out, and I'm going to probably e-publish it first. But then I'm going to probably have to finally publish it with actual You know, like it or not, I'm gonna have to make it a real hardcover book. You know, because it's really, really pretty. And I did a lot of the illustrations myself. I think it's really nice.
I've seen some of them. They're gorgeous. Are you ever gonna? Well, yeah. You're gonna have to do a promo show for your book.
Oh, I guess I will, huh?
Yeah.
Yeah.
Oh, definitely. And I don't know if you're gonna do like maybe like a pre-order thing. You could have a special live event and show the illustrations. They're gorgeous, and I don't know. See if, because I mean, obviously you can see exoplanets with your telescope, right?
Well, no, we can't even see exoplanets with the telescopes that are in space. You know, they don't.
I just assume you can see everything. Sorry.
No, it's like no, you can see. No, it's not that. Telescopes are great and wonderful, but no, you can't actually see. You can't actually see things like that because they're so far away. Remember the scale that I told you about? I'm moving the telescope now, so let's just go back live. So here's a live view. Let me just see if I can bring us to a neat location here. Get the.
I think it's a lack of my math skills and my poor vision. I have like no concept of like measurements or perception or anything, so I figure, I don't know. You can see planets, why can't you see everything else, you know? You can see
that's because the planets are
nebulas and...
Yeah, they're just not... The planets and so forth, they're not as visible. You're not going to see them, I mean, because they're so small. They're just so small. You're not going to see them. I hate to tell you, but they are. Alright, let's try.
But you can when you get the populated universe from North Antonio.
Thank you. That's kind of you, thank you. When it comes out, yes. Here's a 2-second shot at 25,600 ASA. And you're going to start to see in this photo, you'll start to see a little bit of the convolutions of the Milky Way showing up. And you start to see that it's going to look a little more grainy to you. That's not the film speed, so to speak, the sensitivity of the camera so much as we're actually seeing in the center of the image, there's actually a reddish object. That reddish object is actually a nebula, which you can't really see too well, but that nebula is a fairly famous nebula. It's a nebula that actually is the target for many amateur astronomers when they do photography, and it's called the North American Nebula. And seeing the North American Nebula and actually imaging it are really incredible because it's really bright red, has some red in it, and you can see that red in there. And what we'll do is we're going to take a little bit longer exposure. I'll leave the sensitivity at 25,600, and now I'm going to go to a full 10 seconds. So this will be the longest time you have to wait to see something today. So it's starting now, it's counting to 10, and it's going to take this exposure. And the guiding...
What's the longest you can take? 10?
Well, no, I can take exposures of hours if I want to. Yeah. But I typically can't. Okay, this one didn't actually show it too well. It actually ended up getting... it was overwhelmed, so I didn't get it. But you'll see that in a sec when it comes up. Maybe I can catch it by... my whole observatory went white because I actually kind of overwhelmed everything. So I'm going to actually move a little with the telescope. I'll move a little bit and then a little down. Oh yeah, this is... Okay, now it's going to go up a little and over. Let's see. That may help us. I'm going to do another exposure. I mean, I like the, it's fun when you're just out in the observatory and you're just doing these little things. I really like this because it's so much fun. Do a 4-second exposure.
I mean, you could just like close your eyes and spin the telescope, and anywhere it lands is going to be just filled with incredible things, you know, like...
Yeah, I mean, this is a small patch of sky we're looking at, you know. When this image comes up, in a few seconds, you'll see it's a small patch of sky.
Uh-oh, are you there?
Am I still there?
Oh, okay, you are now.
Okay. Yeah, I knocked over my, I knocked it over one more time, and I ended up getting rid of the power. I kicked the power out. Sorry. That's me, my fault. Sorry.
Maybe fix the echo.
Huh?
I said maybe fix the echo.
Or made it worse. Yeah. So
I think losing power is about as bad as you can get, so...
yeah. That's
Okay.
Well, do you see this image now?
We see the image, yes.
Yeah. All right. So this is a star field right near Cygnus. It's beautiful, and you know, look at the colors. You know, the camera's rendering these colors very accurately, and it's just full of these dynamic colors. And you know, the colors of the stars is actually the name of a book, and it's really, you know, incredible because the book has an awful lot to say about the colors of these stars. And right now, just so you understand, we're looking at the Milky Way in the constellation Cygnus, but it's actually not very high. It's still in murk. We're not even seeing it as good as it'll be. So this is kind of interesting to look at this like this. And it stands, it's a good thing to discuss because one of the things to talk about is that when stars are actually low in the sky, you get something called extinction and reddening. And reddening can occur when you have atmosphere between you and the star. Just remember what reddening is with our sun. It's called sunset and sunrise. Okay? And sunset and sunrise is something that you know, is caused by the reddening. It's caused by all that atmosphere between us and the sky, and the star. And that's beautiful. I'll show you. You'll see it in a second. When the sunlight is going through so much sky, so many atmospheric molecules are hitting it, that it actually ends up scattering the blue light that is coming from the sun. You have red, orange, yellow, green, blue, indigo, and violet light. And you remember that by saying Roy G. Biv. Because red, orange, yellow, Roy, G, and Biv, B-I-V. And those are the colors of the rainbow. And the atmospheric molecules are very good at absorbing that blue light from the sun and re-radiating it. And it does that all day long, and that's of course why we have a blue sky. All right, we see blue because of this interaction with the atomic nuclei that are, the atoms which are absorbing the blue light from the sun, and then very accurately, or very efficiently reflecting it back in every direction. Not reflecting it, but emitting it back into the sky. So you get this blue light, and they do that when the moon is out. That's why when the moon is very bright in the sky, it looks like it's blue, has a blue halo around it. It's a mini blue sky, and you know, and that is called Rayleigh scattering. It's a scattering effect that's caused by the atoms in the atmosphere, and when you go through when they have an opportunity to do more of that, when there's more atmosphere between you and the star, then the star's light is more reddened. We see it, like I said, at sunset and sunrise with our own sun. With stars that are lower to the horizon, like the ones we're looking at here in this imagery, we're actually getting the same thing. So there is some reddening being caused by our atmosphere. That's one problem. Another problem is what I said before. That's something called extinction, where the light from the star is actually, I'll say it this way, extincted. That is to say, not rendered gone forever like the dinosaurs, but it's attenuated, reduced in the amount. It's not reddened, it's actually reduced. The brightness of the star getting to you is lowered because of the atmosphere between you and the star. That's called an air mass in astronomy, and we say, well, you have to measure the air mass, and it differs, as you can imagine, whereas near the horizon, the air mass is thicker. Whereas directly overhead, the air mass is the thinnest it can be. But it does have a discrete value. Anytime you do a work that involves trying to figure out brightness of the stars, measuring, say, light curves from a star, like trying to find planets, you have to measure the extinction, and you have to know that air mass. You have to know the reddening that's occurring from our atmosphere. You have to apply all of those to your calculations. Beyond that, you also have to know what's going on at the star. You have to know, is the star in a cloud of gas or dust? Because if it's in a cloud of dust, its light is reddened. Again, and so the light from the star coming from the star, if you're trying to figure out what type of star it is in that OBAFGKM, or be a fine girl kiss me scale we talked about, the difference between calling it a B9 and an F or an A0, okay, could be confused by the fact that it's in, say, a cloud of dust. It might look like it's a little more red, and so and I say toward the red, not red, but a little more red light. And that would make it, say, not look like a B9, but maybe an A0 or an A1 star. And you'd get its spectral class wrong. So you have to know exactly what you're looking at, and exactly where that star is in the sky, and whether there's clouds of dust around it. And that comes from infrared studies. That comes from all kinds of other studies that get done to figure that out. So it's a long-term, study of the sky to understand it. That's in a nutshell what we have going against us, trying to observe from underneath a shell of atmosphere here on the planet. Once we get up into space, we don't have to worry about atmospheric extinction, atmospheric reddening, atmospheric parameters at all. We just have to worry about interstellar extinction, from light from being inside a dust cloud that a star might be in. So that's why it's so much better to actually have satellites from which we would do all this. So, any questions?
Oh, I have a million questions, but like I said, I don't want to dumb down your channel too much, so.
Oh, well, I would think that, if you're asking, probably somebody else wants to know too, It's not a big deal. So.
There's so much information, and that's what is so great. I mean, yes, you doing this live gives people the opportunity to ask questions, but I get to actually go back and listen. I haven't listened to last night's as of yet, but I'm learning slowly but surely. I'm getting there, and more is making sense, and I really appreciate it. But wow, I mean, it's going to be exciting. Because it's kind of like a race to prove your theory right. Like to kind of, I want to be the one that thinks outside the box and figures this out. Because, like when I keep saying, oh, well, it's a different color. Like I was thinking when you were saying like the meteors.
Yeah.
Being different colors because of the elements they might be burning off or whatever. I hope I'm phrasing that right. But then too, so now I'm like applying it to all stars, but then you're like, well, no, it could be the heat of it. So you got to take that into consideration. Now you have the atmosphere, now you have dust clouds, and it's like I don't know, it's like a 3D map where you're like going deeper and deeper, and I don't know. It's got to be exciting.
No, it is, and
it's a little overwhelming to me right now, but
yeah, it's overwhelming to a lot of people. People don't always know. They don't always know what the best thing is going to be for this. They don't know the best approach, so they can stumble around in the dark trying to find the right approach to finding out like the parameters of a star that they're trying to find. Okay, but in the end, your best approach is to just follow the science. You do the scientific approach, and that's something that we've been doing for a long time. It's something I've been doing for a while, and I just think that it's very important to follow the science. It really is. And just use scientific method, because that's actually very important. Scientific method is probably the most important thing we could do. And honestly, if the scientific method wasn't used, I don't know what we could do. I don't know what else there is.
Well, I was listening to an analogy a while back, and they were saying, like, if you burnt all the books in the world, and, no more internet, nothing, and we went back to, like, prehistoric times, in a few hundred years, all the science books would come back, because all the same tests would prove all the same things, and it's just, you just gotta kind of make those jumps to, we can't answer this, but have we tried looking at this crazy thing,
Well, that's like, yeah. And that makes sense, because sooner or later, people are going to realize that the science we know is there for a reason. We didn't actually invent the science. We just figured out the secrets. And we wrote them down in our language, our particular way to translate the universe's secrets into a language. The universe doesn't have a language, okay? There's a syntax to the universe. The universe has a syntax it speaks, and that syntax is math. It speaks math, right? But it's also a case that, the universe also speaks to us in other ways. It actually, it has a syntax, but then the science of the universe is something that we ourselves have to actually learn better. We don't know all the science there is. As it is, we know 4% of our universe in general. We don't know any more than that. And everything we've done, all the amazing accomplishments we have created and followed through with, have been done using simple 4% knowledge of the universe. So that's something that is really important to understand. It's really important to understand, and it's something that a lot of people don't get. A lot of people just won't understand, because that 96% we don't know, that's something that is incredible for us to even try and comprehend. Never mind the fact that it consists of dark matter and even moving again, and dark nebula. Dark energy. Dark energy is something that's really, it's dark only because we don't know what it is. It's not dark because it's black. And so dark energy is something that's coming along, which is, really sort of taking us for a loop and kicked us around a bit, because dark energy is the understanding of dark energy is that dark energy is something that has come from a lack of understanding of what the true nature of this particular substance is. And when we look at, for instance, the universe, we see that the universe is accelerating outward. It's not expanding outward and at a gradual rate or whatever. It's actually it's accelerating outward. This is something that was a finding that was unexpected, right? And that acceleration outward, there we go. That acceleration outward is something that is the result of the true nature of our universe. We are finding that there is something on the outside of the universe we know, the outside border, that is sucking the universe outward more and accelerating it outward. This is phenomenal. And that's something that was a totally unexpected result. Absolutely totally unexpected. So I want to show you this object now that the moon's enough away. I can show you, and this will be the last object for the night. This is something that is like the ring nebula that we saw. This object that you'll see on the screen, do you see it yet?
I do. It's like a turquoise kind of.
Yes.
Almost looks like a cloud kind of.
It does, but it's actually, this is called a bipolar planetary nebula. And let me just jump out of the picture for just a minute. And I want to make sure I see where it is. I see it, and I'm going to try and bring it down a little lower into the view. So sure, go the opposite way, dumbass. That's just a smart thing to do. I just called myself a bad thing.
Put you in timeout.
Yeah, I know. I'll be in timeout.
It's pretty though. I like the colors.
Yeah, and you know what? To us astronomers, things like this are just miraculous because they tell us a whole lot. And
Well, just looking at it, not knowing what it is, the light part, well, it's gone now, but the light part in the middle looks like it's kind of going, like, I don't know, almost diagonal on the screen. Like, it's being pulled, like, left to right, and then the darker part looks like it's being pulled, like, up and down, if that makes sense.
actually, very good. And when you look at it again, I'm taking a 6-second exposure of it now. Okay, and now I'll put it up on the screen. The moon is still out, so it does cause it to be a little bit bright. But we're seeing quite a bit of detail in this object, and I want to share with you what you're looking at when it comes up. This is actually called the Dumbbell Nebula, and it's called that because it's actually shaped like a dumbbell, a barbell. And you notice that the shape that you actually see is akin to an hourglass. And that hourglass shape is because this is a nebula that is a dying star that was actually it's a dying star that actually had an energetic outburst through its northern and southern pole regions, and so that's why you see this sort of hourglass shape. The star burst to the left and to the right in this image in a little bit, and then what I'll do is I'll just zoom in on that just so you can see what it looks like. Let me go back to this and do this. Okay, and just pop out, I'll come out a little bit from that because that's a little difficult to see. That's good. So you'll notice it has a little bit of a reddish tinge around the outside edge, just like the other one we saw, the Ring Nebula. And this is actually a nebula that also has a central star, which is muddied by other stars, and it's had that ejection to the slightly lower left and slightly upper right, just off center, and you can see that, and you also see some knots of cloudy material within it, and that's all in there. That's actually really there. And this is a famous object, not to be confused with a comet. So you know, it's in Messier's catalog. It's Messier 27. Okay, and M27 is something that, you know, as a kid we used to go looking for this, and it was really nice. And actually, I just noticed that the photo I took actually had some of the dome in it. So I'm actually going to go and do a drop down the ASA, the sensitivity, but I'm going to up the speed to. I lied. I said 10 seconds was the most we'll do tonight. I'm doing 13 seconds.
Living
We'll
on
see
the
what
edge.
happens. It's going to make things bright. But by dropping down the intensity, or the sensitivity rather, then things should be a little better. So you'll see the screen go black, and it's going to be black for 13 seconds. Meanwhile, the camera's accumulating light. It came out pretty good. Excellent. So now you'll see that. And you'll see a better rendering of this object than we had before. And now you can see that central star very, very nicely. It's actually a little tiny white dot surrounded by a tiny little dark area. When it comes up, you'll see it. And that's the star that caused everything you see there. The star, again, used up its hydrogen gas, shrunk down and began burning helium into carbon and other chemicals, other elements, and that caused it to bloat larger and larger and larger. And then as it did that, it expanded hugely, and it gets to a point where the outer gases on the star were so far away from the star that the outer bloating speed in which it was moving out could not be overcome by the gravity, and it just continued to go. And so that's how these stars slough off their outer layers. And so the outer layers of the star just kept on going, and this is what we got, was this nebula. And because it happened in that really strange direction, you know, the northern pole of the star, the southern pole of the star, you ended up with this bipolar look to it. In any case, I think that this is actually a good place for us to end tonight, primarily because my feet are starting to freeze.
Oh,
You know, and
what does you do for us?
well, no, it's pretty cold, you know, and you know, this is Connecticut, and it is only June, and it's supposed to be freaking hot, and it's not. That's a problem. But you know, like I told you at the very beginning, you always put on a coat when you go to the observatory, and I'm even wearing a hat because you know, you always wear, you know, a hat and a coat because it will get cold, even if you think it won't.
Did you forget your woolly socks?
I actually did not wear wool socks tonight, and that was a mistake, and that's part of the reason that I have to end now. But it is 12:38 my time, so we are, yeah, I think we did do pretty good for tonight. But let me know what you think. I know it's been a kind of a crazy night, but you know, I hope you guys liked it. And
could I get Dan's last question in?
yeah, of course.
He asks, from the light spectrum, can't you predict temperature, then distance, and in quotations, redshift, etc.?
Well, redshift gives you a parameter which tells you how fast something is moving away from you. And it is true that the redshift, when applied to galaxies, we see that the redshift changes with the distance. And that is sort of a distance marker for us. But within the galaxy, you know, redshift is actually more akin to something else we use called radial velocity, and the stars coming toward us or moving away from us will be shifted slightly toward the light toward the blue as it's coming toward us, and slightly toward the red as it's going away from us. What we see here on the screen is not something coming toward us and going away from us. That's why it's red and blue. That happens to be the spectrum of the colors, the spectrum of the elements that are being chemically that are actually interacting energetically with the star in the center of this thing that you can see. This is the redshift is more for galaxies. We see galaxies that have a high redshift, they're moving away from us at a faster rate, and that tells us something about their distance. And you know, all along we really didn't really understand that until we realized that, you know, the universe is expanding outward in an accelerating manner. Now these redshifts make more sense to us. So it's really an interesting, a real interesting thing. So it's the redshift, as I said, that doesn't matter. As far as the shifting in the spectrum, in the star's spectrum, that has to do more with stars, say, that's being pulled by planets around it, and then it'll wobble in its orbit, you know, as it's moving through space, I should say, and the star wobbles, you know, along, and as it wobbles along like that, you'll see that the star sometimes moves toward us and maybe away from us, and its light gets shifted toward the blue as it's moving toward us, as I said, and red as it's going away from us. And those shifts can be calculated, and that tells us something. It doesn't tell us the distance of the star, but it tells us how fast it's moving, and that tells us something about what's causing it to be doing the movement. Like, okay, that could be a planet tugging on it. And then, you know, in general, we see a transit where the starlight is being where the starlight is being dimmed by a object of some kind, and that dimming that we see is the result of a object moving in front of the star, and that object moving in front of the star could very well be a planet. And then we usually confirm all that with a radial velocity measurement. So that's kind of what we do when it comes to this stuff. So I don't know if that answered it. I think it did, but you know, let me know.
I think it's
I mean, and I'm speaking for chat now, we cannot thank you enough. We love this. And when are you going to be back? Any big plans this weekend?
Yeah, I probably gotta do that. I'm actually looking right now to see if, I never say die. I mean, there's like always something else I want to show. Just always one more thing, I'm not sure that I'll be able to do it. The one thing I wanted to show you, the one last thing I wanted to show you is I'm still way in the murk, and it won't look very good, unfortunately, if I can see it all with everything going on. But I think we'll end on the dumbbell here, because I have to remember that my feet are freezing. So
yes. Yes.
So I want to thank everybody, and I hope you had a good time. If you did, let me know. And if you didn't, let me know.
We got 33 thumbs up,
Awesome.
0 down, only 1 troll. Sorry to chat if I missed anyone's questions. I was trying. Great questions, thank you.
Cool.
And my God, thank you, Mark, for answering them all. And it's not just like a quick little answer. It's an explanation, and that's where the knowledge comes in, and that's why we will all keep coming back.
I appreciate that,
Yeah.
And I'm happy to have you guys here. Thanks for coming in, and you're welcome, by the way, for those that are saying thank you. And I'm sure that as we move forward, I'm going to be able to show you some cooler things, because I'll be honest with you, the spring sky is really boring. Okay, and we're in the spring sky right now. It's the most boring time of the year. So if I was thinking, I probably would have started this stream in August, when we have Milky Way and all kinds of things to look at, and then fall and winter approaches, and we have Orion, and we have the Pleiades to show the nebula around those and stuff. But hey, the bottom line is, any time of the year we have things in the sky to see. And if the moon's out, we can see other things too. So I like that. I'm glad that you guys joined me, and
I think you did it right this way, because I think from now until August we're gonna get like a better. Well, I mean, people like me, like some people already know this stuff, and they're just here for because they love it, but like
it kills some time.
The knowledge I'm gonna learn, and I mean, even if I get like a % of what you're talking about, that's gonna be huge. And then I will know what you're talking about when we're seeing these things that everyone's gonna be blown away by. Like, I don't know. If this is boring, I can't even imagine, because this is incredible.
Well, here's what we're going to do. I mean, everything I'm telling you about, all these things about the stars, all these things about these nebula, the planetary nebula, the globular clusters that we saw, the giant stars that we saw, the binary stars we saw, the different color stars that we saw, those things are all going to come together as a little family of objects, because we're going to actually do one stream at some point where we're going to actually talk about the how this all works, how these all come together, how these all work together, and why these objects that we're looking at now have such a profound effect on our understanding of astronomy, and it'll be something that'll be very I think hopefully enlightening, because we're going to end up talking about, and I've said this before, and I threatened to do this before on some of the other streams, talk about the history of everything. And this is a stream about the history of everything. But we can't talk about the history of everything until we see everything that I'm talking about. We have to actually see these things, explore them live, directly. Everything you see on the screen is being imaged now as we talk. We're not imaging these things and just like showing you a picture. There'll be streams where I do that, because I'm going to want to show stuff that we did image in the observatory, and then bring up a picture that shows how Hubble saw it, how Hubble sees it. So you see the difference in where we've come. But we actually have some advantages here by doing what we're doing, because you're getting to see what it's like, and you're going through the process with an astronomer, who's actually enduring the elements, so you don't have to. But I'm glad that you're here. I'm glad that you're liking it. And,
No, seriously. I mean, imagine if, like, some teachers found this site and brought it into, like, I don't know, like an elementary school. That could be changing the path of these kids' lives. They could be like, I would kill to do this for a living, you know? You are showing them what it's like and getting excited by it still, you know? So,
Yeah, I knew at age 9, though.
I don't know, this is going to be huge.
Yeah, I knew at age 9, you know, that I was going to be an astronomer. I actually, at age 9, I knew that. I had already planned it. I had already figured out, in fact, where I was going to go to school. Now, I actually applied to a number of schools. I applied to Worcester Polytechnic Institute in Worcester, Mass. I applied to Yale. I applied to Wesleyan University in Middletown, Connecticut. I got into Central University in Connecticut. I got into Wesleyan, and I even got into Yale. But I actually chose to go to Wesleyan because Wesleyan University, as my core school, was the school that I felt was going to be the best for me. You know, Yale for me. Yale was in New Haven, Connecticut. And New Haven, Connecticut, you know, it had some bad memories for me because as a kid I went there a lot for, you know, a heart ailment, and so every time I went to New Haven I was always nervous because Yale New Haven Hospital was right around the corner, and it was like made me nervous. So I never got through that too well, so I didn't go to Yale. I ended up going to Wesleyan, and that was really good. Then, you know, I did some graduate school work, you know, in computer science. I almost got my master's in computer science, but I ran out of money and I couldn't do that. You know, my next thing is to get the master's in planetary science, and that's something I'm probably going to do at the University of Arizona. So, you know, I've got a lot of you know, resources now to do that stuff. So I'm not going to sit back and just do nothing. You know, I've got a long way to go. You know, I'm happy with what I do, and I'm happy that I do it. You know, and this is.
We're happy that you do it too.
Well, that's good. You know, that's really good. But I'm gonna. I hope you don't mind. I'm gonna stop the stream because I'm gonna.
I don't want to be held responsible when you catch a cold.
It's already too late. No, I'm kidding. I don't know that for a fact. I'm just gonna pick up my camera batteries, and then. All right. Well, thanks, guys. And
Good night, Kat.
I am going to stop for now, and we will be back. So I will talk to you soon. So.